Well, hello, everybody. Welcome to, I think, course number 8 in our winter course series. I'm Inès Montaño, and today this course is titled Quantum Network Simulation Software. It will be presented by myself and my co-instructor, Jaime Diaz. So let me first introduce myself. I'm Inès Montaño. I'm an associate professor for applied physics and material science at Northern Arizona University. I'm German. My background is in theoretical condensed matter physics. I was at Sandia Labs for a long time. Now I'm at NIU. And I think that's really it. Oh, and I'm in Thrust 1, which is the network thrust for CQN. And I'm also the director for the engineering workforce development. Jaime.
Hello, everyone. I'm Jaime Diaz. I am a grad student here at Northern Arizona University, a part of the Applied Physics and Material Science program. I got my bachelor's degree in applied physics at California State University, Channel Islands. And I also worked with Thrust 1 and involved with the engineering workforce development.
All right, so let's get started. Oops, let me go to my next slide. Here we go. So if you attended any of the last courses this week, then you have heard already that the mission for CQN is really to build the quantum internet. And you have heard a lot of what this means, what applications we think are connected to this. So during this week, you've heard a lot about the why we want this internet, the what's happening, what do we need, and how we mean to do it. And you've also heard a lot about applications and the key components of a quantum internet, and you've heard about challenges. So you've heard a lot about these cornerstones of CQN, like everything that we're doing is centered around the quantum internet. And so today we want to look at something different, and that's the quantum network simulation software. It's not different that it's a different topic, it's just different in the sense of we're not going to talk about our experimental efforts, we're just talking about ways how we can simulate a network because we don't have one yet. And so why would we want to do this and what network simulators are out there? So I'll have you a list of network simulators. And I'm pretty sure, even though it's very new, the list is already not complete. There are currently always new simulators coming out. This is not meant as a complete list, just a list of network simulators that I'm familiar with. And so I just give you the names and the websites. So if you want to, you can go back and you can look at those and click on them and check them out. The slides, I think Brianna posted the link in the chat, so feel free to download the slides so you can follow along. So they're all very different, these simulators that I've listed here. What they have in common is that they really mean to provide a platform, a way for you to test out things. And I just call it here things related to a quantum network. So what I mean with that is they can be very different things you want to simulate, you want to look at, but we don't have access to a real physical quantum network. We have test beds, but we can't look at everything yet. And so if you're interested in the physical layer, what your qubits need to fulfill, what kind of requirements you have for your gates, or how to best do protocols on the nodes, how to control the network, or what applications, or what controls performance, all of those could be things that you could look at with the quantum network simulator. That being said, I think we could probably do a whole short course just on all the things you could do with the quantum simulator. And instead, we decided to do a short course on how to do something with the quantum network simulator. And this might sound really weird because it says just something, but the reason for this is there are just so many different things you can do. And so what is useful for you might be different for different people in this group, but we just wanted to look at things that you can do with the quantum network simulator that might be useful for many people to get started with working on this. So this brings us to who this short course is for, who is meant to be part of this, or who did we have in mind when we designed this course. We really see this as a short course that is for anyone who is interested in learning how to use the quantum network simulator. So if you are someone who has a lot of computational experience, that's awesome. It'll probably be much easier for you. But if you're someone who really rarely programs, we hopefully have designed it in a way that you can still get a lot out of this course. Why might you want to work with the quantum network simulator? You might be interested to just use it to explore some concepts. Maybe you read a paper and you want to try out how this would work, or you might be thinking about integrating it into your research, driving what you're working on, or maybe you just want to have fun with it. I personally think it's really fun to work with these, so hopefully you will find this as well. And this brings us to the idea we had in mind. So our goal is really to hopefully have this designed in a way that this short course can help you get started. So we're not saying after this short course, you will be ready to tackle every problem, but hopefully you have learned enough and have enough material from this short course that the bump that you might experience when you're starting to work with a simulator is lower, and that it helps you to do something that you consider useful. So if it's developing a protocol or looking at physical requirements, that might be different from person to person. So this brings us to the core module of this course. So we call this the simulation deep dive, learning by doing, and it's really all centered around hands-on exploration. So we don't want this to be a class where we're just going through line of code after line of code and you just try to catch up. We really want you to have a lot of time to really work with this and get your hands dirty. And so we've designed a bunch of networks, of notebooks, and these we designed in a way that we can use them to introduce you to the key building blocks of a quantum network and of quantum network simulators. We want to use them to provide you with opportunity to jump right in and explore something and try out material. And we also have designed them in a way that with every notebook, the material becomes more complex. It doesn't necessarily mean it becomes harder, it just means that we can tackle more complex situations because you're building on the material from the previous notebooks. And then at the end, we have chosen a teleportation network as the example we want to simulate. Okay. So how to get the most out of this course? It's pretty simple. Like in every class, the more engaged you are, the more you will get out of this course. We really want you to work with the notebooks that we will give to you. We would like you to try to apply the material. And Jaime and I both think that ideally you would want to work with others. Discuss your questions, talk to other people about the material in those notebooks. But not everybody is comfortable doing this. And before we are forcing everybody to go into breakout rooms all the time, we thought it would be a good idea to see how people actually feel about this. And then based on those answers, we might modify our plan a little bit. So we were picturing it that whenever we discuss a specific notebook, we would love for you to join a small breakout room with maybe 3 to 5 people tops, where everybody works on their own notebook, but you can unmute and you can discuss and you can say, hey, I don't understand this line. You can just work together. But if that's something you're not so comfortable with and you'd rather just work on your own, stay in the main room, that's fine. We would just like to get an idea how many people would be open to joining breakout rooms. And so we have this poll, which is launched, I think, right? I see it. So do you prefer to work alone or are you interested in working with others? And so I should probably point this out. It doesn't matter how much experience you have. This is not going to be in a way where if you were a novice to computing that you just don't know where to start. They're supposed to be helpful to get you started, but it's still usually a good idea to discuss with others what they think this means or if you're stuck on a certain part.
Maybe we'll give the poll like another minute.
We're at 80%, it's pretty good. So I think it looks like the majority of people would not like to work with others, but rather would work on their own. And we have maybe 15 people who would be open to working with others. Does it sound roughly right to you, Jaime?
Yeah, so on the poll right now, it says that 14 people are interested in working in a breakout room.
Right. So maybe we'll make 4 or 5, maybe 4.
Yeah, I'll make a few breakout rooms.
Okay. That sounds good. All right. You can end the poll. If you want to take a look real quick, you can share I guess I could share the result. I think I shared the result.
Yeah.
So you can see that's your breakdown. So Some of you are open. I think that's great. But if you'd rather work on your own, that's totally fine. Okay, let me close this here. And then let's keep going. Okay, so going back to, we want this to be something that hopefully gets you started so you can do something with these simulators. And this was the list of simulators, and we could have picked any of them. They're all really, really great. We picked NetSquid, and I feel like I should really put a disclaimer out here. This does not mean the other ones aren't great. The reason we picked NetSquid was because it's very well developed with a lot of supporting material, and I think it's a good one to get started with. It doesn't mean the other simulators aren't awesome too, and we actually discussed for a while if we should go with NetSquid or another one. In the end, we chose to go with NetSquid. So what is NetSquid? Here's the link. This is the link to the page. So NetSquid is a simulator that was developed at QTech, and it has a very awesome website right here, where you can, first of all, sign up to get NetSquid. It's free. You just have to sign up for an account, and then you can install the software. You do not have to do this right now. I'm just telling you how you can do this if you want to in the future. And then it has really a good amount of supporting documents. So pretty good. That being said, we will have all the simulations in Python, and the simulations will run on a virtual machine that we have set up. So we'll give you accounts to this, so you can just run all the notebooks we're giving you to work on in your browser, on your computer, without having to set up anything. That's the plan. So we will see how the server works and how the server holds up. We've tried it, and all the tests we did look like it's going to be fine, but you never know. Those notebooks are Jupyter notebooks. You might have used Jupyter notebooks before, or you might have not. They're a really awesome way to have documents that allow you to have the code and the output, but also supporting text, equations, images, all in one document. And so these are the kind of notebooks you will be working with. To access those notebooks, here's the web address. So you will go to this web address. Now comes the tricky part. That will be the challenging one for us. So we will bear with us if not everything works right away. We have set up accounts for you that are just labeled user 1, user 2, so forth. We of course need to make sure that everybody uses a different account. So what we're going to do now is Jaime has used the participant list to assign you numbers. So he will go through these numbers and, for example, say, you just pick a random name here, ideally someone I know, so they won't be upset if I call on them Stephen Fleming. So he might say Stephen Fleming is user number 1. He did not say that yet. So Stephen, you're not user number 1 yet. Just saying. He will read those usernames to you. Please write them down. This will be your username. So if he tells you you're user 15, that's your username. And then your password will be short course 8. So listen for your account info and then log onto this server, please. And whoever is joining now, that will be fun because they missed all of these things.
That's okay. I'll start with.
Did you just get admitted? Oh, there's more people still. There are more people still coming. So I'll let you do this, Jaime, and then when you're done, I'll try to catch up the people who just joined.
Okay, so I'm gonna start off with the list that I have right here. Basically, I'm gonna assign you a user account for this Jupyter Hub. It's going to be the word user all in lowercase and then the number associated to it. So here I'm going to start listing off the names. So I'm sorry if I butcher any names here. So user 1 is going to be Ahmad Sulami or Luman or Sulaman. Sorry about that. User 2, it's Andrew. There's no last name, so I think that's the only Andrew with no last name. User 3, we have Austin Hancock. You were just admitted. So Austin, if you can just write down user 3. User 4 is going to be Bob Lance. User 5 is Brett Green. User 6, Dan Kilper. User 7, David Blue. User 8, Dennis McNulty. User 9, I'm not sure if this is all one word. It's DKILBANE. Awesome, thank you. User 10 should be Evan Dowling. User 11 is Gong Yu Ni. User 12, Hazel. User 13 is Jaden Brewer. User 14, I'm just gonna spell this one out as well because it's all one word. Jazryc. If you can just give me like a thumbs up, that'd be awesome. Inès, do you remember what number was right there? I think that was 13.
Which number was not working or which number you just covered?
What number I just said?
I don't know.
Okay, I think that was 13. We'll just keep going. It's okay.
JZRYC, maybe you can put it.
13. Oh, thank you, chat. I heard you. I see it. User 14 is Jerry Horgan. User 15 is John Kim. User, so that's 13, 14, 15. So user 16 is João Batista R. Silva. User 17 is Justin Garrigus. Thank you. User 18, Lynn Lee. 19, Marco Ruffini. 20 is Miriam Afzari, sorry about that. 19, Matthew Brown. 20 is Melinda Andrews. 21 is Mengjun Si. 21 is Meni Merzuki. The last name is oh, thank you for the thumbs up. So 23 is Murali Venkat. 24 is Naryanan. 25 is Nayanan. Or Nayana. We're at 20. Sorry, once we start listing these names, I started to lose count here. So I think we're at 23, if I remember correctly. 25, thank you. So 25 is Nushin M. Escatri, thank you. 26, Pao Kang Chen. 27 is Pavala. 28, Pedro Medina Gonzalez. 29 is Pratik. 30 is Rick Team Bowmick. I think we're at 31. So 31 is Sandy Zhao. 32 is Santanu. Thank you. 33 is Scott Allen. 34 is Silicon Arts Mark Prouston. 35 is Stephen Fleming. 36, it's Steve, no last name. 37 is Tom Bell. 38 is, sorry if I mispronounce, it's Yu Zhuan Xu. Spelled Yuxuan. And lastly, I think this is 38, Zachary Spengler. And let me just make sure I didn't miss anyone. So does everyone have their Everyone should have a username associated to them.
And we have uploaded the notebooks to a lot of accounts. I'm not sure to every account because there were more people than we expected, but I will also put the notebooks into the chat right now. So if you end up not having them uploaded yet, or if you would like to use the notebooks locally on your account, on your computer, because you already have NetSquid installed. Sorry, I'm trying to post them, but when I get a direct message, then it just sends it to the one person. So we do that. Jaime, do you think every account we just went through already has all the notebooks up there, or might there be?
The last maybe 10 or 8 or 10 probably need them to be uploaded.
Okay.
So
I'll just add
31.
the first 3 in the chat, but let me keep going for a second so you can see what you're supposed to see. And
Inez,
then,
we have some people who are on secure networks and aren't able to connect to reach the content.
they can't get to the server, or they can't get to the information in the chat.
To the server.
Okay. Can they get the notebooks from the chat?
Let's see. Can somebody confirm if they're able to download directly from our chat? No, they are not.
Okay. I can also, or maybe Jaime can real quick send Brianna the notebooks.
Yeah,
Okay,
I'll
and
send
I
it to Brianna.
Post them on the website so they can get them this way. And then what we can do is if maybe everybody who cannot access them, so then they won't be able to run on their own. I mean, run them on their own if they don't have NetSquid already. We can have them all be in a breakout room where maybe we run it. We'll figure something out there. So let us know how many of those people have problems that they will not be able to access because they can't access the server. So if you were able to access the server, what you should see if you're one of the lucky first 40 or so is this here. So you see something that's called Jupyter Hub here. That's where all the files are. And then you should see these A to M notebooks. And I have already put A to C in the chat. And I think Jaime is emailing them to Brianna. So Brianna will post all notebooks also on the website. So you can also get them from there. If at any moment when you're working with the notebooks, you ever see the server not running message, that happens, just click launch server and you'll be good to go. And if you have any other problems at any point, let us know.
Yeah, and I did receive a few messages that people or one person is having an issue. I'll look into it in just a second. I just need to send the files so the others can have the information.
Right. And don't worry, there's actually nothing for you to run yet. So we just wanted to get this all done early so everybody can practice getting to this. And if you are on the server and you can click on the first one, which is a Jupyter intro, to just practice how to open a notebook here. So if you've worked with Jupyter notebooks before, then this is all known to you, but we just wanted to make sure that if somebody has not, they also know what to do here. A Jupyter notebook is, there we go. A really convenient way to work. And so this is the one that will come up and you can try it out in a second, but let me explain to you all the parts in a notebook. So the first one here, this here, whenever it says in, those are the cells, this is where your input goes. And the input can either be code, can either be code, so those are the commands for your Python, or they can be markdown, which is awesome to have like explicit illustrative text or equations or images. And you set the format for your cell right here in this box. That you click on this and then you have the options. And you really probably will only use the code one. We used markdown a lot to give all of those comments in there. So the input goes in here, then you set your format, and then in order to run an actual cell, you just either click on run or you can click shift return. But the run one works pretty fine too. And then you would evaluate whatever is written in this cell. So if it's text, it will just look prettier. If it's markdown text, or if it's code, then it will perform this part. If at any point you want to restart the simulation and remove all the output, I do that a lot, then it's a good idea to click on kernel here, and then you have restart and clear output. That will take all the stuff that was output, all the results, everything will be removed, and it will look like a brand new notebook. So that's pretty good to know. So again, for whoever joined later, it's probably a good idea to download the slides. They're on the website. Brianna posted them, because then you can go back to these parts if you're new to this, and you can look at these instructions. And then very last, if you want to run the whole file at once, I actually don't recommend it, because we really want you to go through things cell by cell here. But if you want to, you can push this little button up here, and then it will go through all of the file, all of the content of the file in one setting, so you can see everything at once. Okay, so this brings us back to this list of notebooks here. So let me walk you through why there are so many and what the idea behind those are. So you can see there are 3 chunks. So there are chunks on quantum memory, there's a chunk on quantum processors, quantum channels, and quantum networks. So those are really the big groups that we have in mind that we want to cover here. In the chunk on quantum memory, you will work very much on the basics, and it's not even so much that it's that this is like specific for a quantum network. A lot of this is just quantum. You could do all these parts also with other quantum simulators, but you need to know how to do them in a network simulator to do the rest then later. So this is also a good opportunity for you to practice trying out some of the material you learned about before, like how to actually change the state of a qubit, how to entangle qubits. And so this is those are the things we're going to work on in these 3 notebooks. So we will learn how to store a qubit in a quantum memory, how to change the state of a qubit by applying gates. We will peek at the state of a qubit. That's of course not something you could do in real life, but it's so awesome for learning and debugging, because it just allows you to see if the qubit is really stored where you think it is and what state it is in. So it's a really cool tool to have here. We will also practice how to entangle qubits, and we will do a local state teleportation. What I mean with this is we will teleport the state of a qubit between 2 qubits within the same memory. So they would just be close together, so you don't have to go through a channel. They're just right there. Then we will practice how to use a quantum processor. So this means now we have physical instructions. So when we are applying a gate to a memory, to a qubit, we will take into account how long applying this gate actually takes. If we can apply it to every memory position, so that's topology, we will account for the operation times, like I said, and we will also, because we're doing this, then switch over to using the discrete event simulator. This is something that SQUID does to take into account that the states have to be changing. So the way this works here is, and I'll come back later to this, you will have your system will be in a specific state, and if nothing happens, the state doesn't change. But then if you do something like move a qubit, initialize a qubit, apply a qubit, or there's a qubit going through a channel that takes a certain amount of time, then the time will be advanced to the next event, and this will change the state of your system. And then we'll also work with quantum programs. In the next chunk, quantum channels, we will work on practice on how to work with nodes, so processor and memory, and also how we can communicate between nodes. So we talk about input and output ports. We'll talk about classical channels and quantum channels, and very useful, we will talk about node protocols. So how can we structure easily all the things that a node will have to perform. And then we have our last one. This is really where everything is coming together. So this is how you practice how to simulate a full network. And it's still a simple network, but it has really a lot of these components that you would want to have to jump right in. So we'll have the nodes connected by channels, we'll have quantum programs and node protocols. And we will also look at how something will change when there are actually errors in the system then. Okay, so let me go over the example that we chose as our key example that everything is centered around. So from the first short course by Mike Raymer on Monday, through many of the others, you've heard about quantum state teleportation, where you have, so I don't call them Alice and Bob, I usually call them Agent A and Agent B. Everybody has their reasons. I know traditionally it's Alice and Bob, but then Eve is always the bad one. And so for us, we've always been doing Agent A, Agent B, and Agent E. So Agent A has this qubit that's in the state smiley face, and the goal is for Agent A to send the qubit to Agent B. That's then quantum state teleportation, if that really works. And if you are not so confident in the steps for the teleportation, I will go over them here real quick. So that's my state teleportation refresher. So we start out with Agent A and Agent B sharing an entangled qubit pair. So you've heard about entanglement in previous lectures. And that's really a key resource for building a quantum internet. And so something we will need for quantum state teleportation. And then agent A also has this qubit in the smiley face state. And the idea is that agent A doesn't know the state of this qubit. And so the state is supposed to go from agent A to agent B. Whoops, there we go. So how does this work? So the first step is agent A performs a joint or a belt state measurement on the local qubits. And we will talk about what that means and how you do this. And then in step 2, so you'll see my steps go upwards. So the oldest step is at the bottom, and then I'll go up here. So when this one is checked, this means the qubit now, with both qubits here were measured. And so we have classical bits that are the results of our measurement outcome. And now agent A has to send these measurement outcomes to agent B. And so I have my little envelope here. So in a network, that would be a classical channel. And once agent B has the classical bits, then agent B will use these bits to correct the state of the local qubit, so that as a result, this state now looks like the smiley state agent A had in the beginning. So that's the idea. And I'm not getting any comments in the chat or Q&A, so I'm hoping Brianna and Jaime, I don't know if you get them and I don't.
Yeah,
but
I'm getting them right now. We're having server issues, so I'm seeing if I can fix it.
Okay, and
So
we'll
right
take
now, I think the server is overwhelmed, so it's crashing. So I'm trying to fix that.
That's fine. And so people, if it's not working, just bear with us, and we have backup plans, so we can come back to this. Okay, so let's talk about the teleportation refresher some more. So this was the traditional teleportation protocol where the state of this qubit gets transported from agent A to now at agent B. There is another way how you can look at this. You can look at this just like having 3 qubits, and you just want to teleport the state of one qubit to another qubit. So not really caring about where those qubits are located, they might be together. And how would you do this? So let's go over this one. That's then more teleportation circuit. So we have these 3 qubits here. The smiley face is the qubit where we want to teleport the state. And then we have 2 other qubits that are just both in the 0 state. And now the first step is to apply an H and Hadamard gate to qubit 2. And if you are new to working with gates, all the information about the gates, how to look at them as a matrix, are in those notebooks. Not so much about what they do, but at least the command to do them and the matrix representation of them. So you apply a Hadamard gate, and then apply a controlled NOT gate. And so if you have both of those together, the outcome is that these 2 qubits here now are entangled. That's what I assumed in my step 0 up here, that they would already share an entangled qubit pair. Now I actually entangled the qubits on the fly. And then in the next step, we'll have a C0 gate and another Hadamard, and then measure. And these 3 steps together, this is this joint measurement that I was talking about here, this belt state measurement. Those are these 3 steps together. And then depending on these outcomes, we apply correction gates. So if the outcome of the measurement on qubit 2 was a 1, we apply an X gate. If the outcome of the measurement of qubit 1 was a 1, then we apply a Z gate to this last qubit. And by doing this, we then recreate the state, the smiley state on this qubit. And so there are these 3 chunks to kind of help with this again, to see these 3 groups. So the first one was entangling the 2 qubits that are up here, really used as a starting condition. Then the belt state measurement to measure the 2 remaining qubits on node A here. And then last, the correction parts. Okay. Oops. So let's look at this one first. If we just want to do a teleportation from one qubit to another qubit, and we don't care about this really being in a network where they are on nodes and they're living far apart, but we just have 3 qubits and a processor together in a quantum computer, we want to do this. What would we need? So we really would need a quantum memory, which means we would need a way to store those qubits, right? Because we have to manipulate their state. So we have to be able to store them ideally without any errors happening. We need a way to manipulate the state. So for example, change the state of this qubit here that's in the 0 state to a superposition. And I know we talked about superpositions in some of the previous modules. And so we do this by applying gates. And then last, we need a way to measure qubits. So those are all the components we would have to have in order to actually teleport a state from one qubit to another. And so this is now where we are coming to the part with the self-contained notebooks. And before we go into this, I say we'll do a quick 5-minute break to see if we can get the server issues solved. But let me go through real quick how these notebooks will look first before we do a break. So those are all things you can still do just by downloading those notebooks on your local computer without running them. So in every one of these notebooks, you see some color coding. So we did really try to make this not as daunting. And that's what's so cool about Jupyter notebooks. So the title, right, that's the summary of what's happening here in blue. So in this notebook, in this first one, we'll practice how to store qubits in quantum memory, how to change the state of qubits, how to peek at qubits. Like I said, that's not physical, but so convenient, and how to measure qubits. And then you will find little gray boxes. Those are the code, the Python code. So we tried to comment in the beginning a lot. Later on, it's not so much because we're assuming you're starting to see the patterns there. So first we have to load all the content from the NetSquid package. So this is the part that then wouldn't work if you don't have it installed and you can't run it on the server. So these instructions won't work. And then you have these yellow boxes here. So the yellow boxes, those are really the boxes where we're giving some background information. And actually, I just remembered that I made my life easier and I forgot about it. So let me go through those. So blue box, quick summary of notebook. Yellow boxes, those are the new definitions with default settings. So that's something you can come back to then. So if we're using a quantum memory a bunch of times here, at some point you might need to know, well, how do I do this if I want to give it a noise model? So it kind of gives you at least the parameters that you can give to this class. And NetSquid has a really awesome documentation where you can find a lot of information for all of these components. We just wanted you to see the defaults. So for the quantum memory, for example, the default is that it's initialized with 1 memory position. And if you change this number, you will change how many qubits you can store. And then we have these inputs here. So those are the code cells, right? So this is the code that you would actually run. You can run all of it, but this is the stuff where the calculations are then happening. And to do this, remember here, you click on run. So you would first click in the cell, then click on run. And then before your code has been run, so before your notebook has been running on the server that has NetSquid or your computer which has NetSquid, it might look a little funny. And what I mean with this is, so there is this text, like in this case, let's apply the xk to the qubit. So that's what we want you to do. And then we show you how to do it. And here it says like print the state of the qubit. And so when you evaluate this cell, this state will print. And then this text afterwards would talk about what you see. So we know what's going to happen. So the text is already there. So if it's not run yet, it might look a little funny because some of the code hasn't been run. So it might look strange. Once you have run it, the output shown then makes the text hopefully make more sense. So in this case, the code was run. So the state is here. Here's the state printed. And then you can see, okay, this really corresponds to this. And in this case, here too, there is the state. And here is the text that goes with it. If you ever see the input with a little star instead of a number, it just means the code is not done running yet. Okay. In every notebook, except for the last 3, you also find practice suggestions. So this is the part that then will not work if the server problems don't work and we can't have people actually run them. The rest we could still work through, but I can also go through them on my computer. So the practice suggestions, those are ideas for you to try the material that we show you in the notebook on your own. So for example, if the notebook showed you how to initialize the quantum memory, which can store 1 qubit and then apply an X gate, then maybe we suggest that you do this on your own and apply a Y gate. And so there are just some ideas. So if you want to try it out, you don't really know what to do with it, hopefully that will help. And this brings me back to how to get the most of this course, right? So try to be as engaged as possible. It's always hard when you're on Zoom and somebody's just talking at you and there are distractions. But the more you can focus on this, hopefully the more impactful it will be. Ideally, work with those provided notebooks, try to apply the material, and then if you're up for it, work with others, discuss your questions. So this brings me back to this example that we talked about. So we said, if we want to do this, we will need these parts and we will want to simulate this now. Sorry, I got distracted by the chat. I shouldn't pay attention while I'm talking. I'm not a good multitasker. So I'll check in with Jaime in a second. We might take a 5-minute break to see what we can do. But the first notebook he will work with is notebook B, Quantum Memory Example 1. And so this notebook is the one where we're just working with quantum memories, changing states, and all of these parts. And so what we will focus on there is we will look at a quantum memory as a way to store a qubit. We will learn that there are different positions we can store a qubit at, and we will learn how to apply a gate to change the state, how to peek at a qubit to see the state, and if it's really in the memory, and how to measure a qubit. Okay, so Jaime, how is the simulator doing?
I believe some people are accessed. I can see that some people are in, but it's really slow.
Okay.
Probably as a result of the server not being equipped enough for 48 people.
So one thing we can do is, so first of all, let's take a 5-minute break. And then if, I know not everybody was open for a breakout room, but what we could do is we could split people in breakout rooms and then have one person run the notebooks in the breakout room. At least then people can do it together. And so if you are, so what I would suggest with that is we would need, let's do, we have 55. How about Jaden is on here too, right?
Yes.
So we could, let's take a 5-minute break for everybody. We'll come back at 9:50 and Jaime and I will go over a few scenarios, and I think we will have a way. So if everything is working for you and you wanted to work on your own anyways, feel free to go ahead and work on your own. Well, other people, if you don't have access to the server or you can't access the notebooks, we will place you in breakout rooms and we will work in smaller groups there so that everybody can experience this better than if I just click through everything on my own.
Inés, can
Yes,
you
and I just, one second, I just got a message from someone. You do not have to use the server, absolutely not. So actually, it would be super awesome if everybody who has NetSquid does not use the server. We will give you the notebooks, use them on your local computer. That will help a lot because then it will leave the server for the people who don't have NetSquid installed. Brianna posted all the notebooks on the website, correct?
I don't think she was able to because of the file type. So I was gonna recommend, can we put the notebooks into the chat for the people who just got here?
I will do this, but I don't know if everybody could access the notebooks in the chat. I thought there was a problem. So I'm going to put these back in here first. And then if you are a person who cannot get the notebooks from the chat, why don't you just send your email address to Jaime and Jaime will email you the notebooks. How does that work?
Perfect. Yeah.
Right?
Perfect.
There's nothing, we will not let this take it. So we were actually going back and forth. At first we thought we would ask everybody to install NetSquid. And then we were like, oh, that's not a good idea.
Yes. So the purpose of the server, the purpose of the server was so that for those who don't have much coding experience, don't have, if you don't have Python because you don't use Python, if you don't have NetSquid, everything should be installed in this virtual machine that you can just access remotely. That way you can still work with the notebooks along with us. I have some people saying they don't see the chat from you, Inés.
I don't know what to do when you can't see the chat.
Okay.
I put all the files and sent them to everyone.
Yeah.
I'm pretty sure
anyone who is looking for to get the files, send me your email and I will forward them to you.
Yeah, so we can do this. So we have a few more minutes of break and then, so yeah, if you do not need the server, just log out of your user account and then we'll see if that solved the problems and we will see how many people we have left who will not be able to run this on their own. And I'm just gonna shamelessly use my grad students. Jaden, would you be okay in leading a breakout group where you run the notebooks on your local computer And if somebody cannot access, they can join this breakout room to work with you. This is the part where you could just put in the chat, yes. No pressure. Awesome, thank you. So that will already be one breakout room. And then Jaime and I can also each do a breakout room. So that's 3. Do we know how many people need access? Should we start with 3?
Yeah, I'm getting emails right now. I only have a handful at the moment. Some
Okay.
people say that the server is starting up, but it's really slow. Some people are able to download the file, so I think it's working for some.
And if you have a total of 13 files from A to M, that's the correct number. The first one was just the intro file. We will just be working with number B, example 1 for the content memory now. And so what I'm going to do now is we will open, that work? Yeah. We will open 3 breakout rooms, or let's open 5 breakout rooms. The first 3 breakout rooms will have Jaden, Jaime, or me in them. And so we will have the notebook open there. So if you want to try something out with us, we'll be in this breakout room. And then this one is a really quick one, the first example. So let's say at let's say at 10, we'll come back to the main room and we'll check in, see how it's going.
Sounds good. Right now I'm working on sending those files to those who are asking for them via
And
email.
I will open the breakout rooms. Here we go. So I'm making 5 breakout rooms. The third ones are breakout rooms that have either Jaden, Jaime, or me in them. And the last 2 are breakout rooms that do not. So if you're someone who has NetSquid locally installed and who's happy to discuss with others, then that would be awesome if you can go to one of those breakout rooms. And I will see you back at 10. There we go. Okay, let's get back to it. So that was the memory, the first example for the memory. So if you're just joining, if you're just coming back, so we will adapt a little bit to the situation. I kind of thought that those things might happen. That's what happens when you're trying to code on the fly, but that's okay. So what we're going to do is going forward, we will, when we have the timer, we would normally have you go into a breakout room or work on your own. I will go through the notebook in the main room. And so I'll go through it, talk through what we're thinking. We won't do the practice, but that's okay. We'll at least talk through it. If you can run everything on your own, either on the server or on your local computer, just mute me and I'll try to wave or something, or just check in once in a while and see if we're still in notebook. You can still mute us so you can focus, or you can just listen while you're doing your own thing. If you would like to work in a breakout room and you're it's working, just join one of the 5 breakout rooms. We'll leave those open. So hopefully that will work. So let's get started. If you have any problems, questions, still looking for the notebooks, just go ahead and let us know. Okay, so then we're coming to the second example. So this is notebook C. So if you have the notebooks, the next example you will open is notebook C, content memory example 2. So in this one, we'll look at belt states. So we will practice how to operate on qubits and how to actually entangle them. So that's a pretty big part. And we'll do this in this scenario. So we'll have a quantum memory, it'll have 2 qubits in it, and we will initialize the qubits. So first we'll place the qubits in the memory, initialize them, and then we'll apply a Hadamard gate. So we get a superposition here, and then we'll have a control NOT gate that effectively leads to the entanglement. And then we will measure the 2 qubits and see what happens. Oops. And so this is the part where I now need to share my other screen. So let me go over here, stop share, share screen, and it's this one. Okay, so I'm gonna close my quantum memory real quick there and then shut it down there. Okay, so I'm gonna open this one here and I will zoom in again. So I'll try to make that big. Okay, does this look okay? Can you see that good enough, big enough? Should I make it bigger, Jaime?
That's perfect.
Okay, all right. So what I'm going to do is I will just go through this notebook and I will run all the cells and talk through what I'm seeing, what's happening here. And you can follow along on the screen. If you can do things on your own computer or on the server, go ahead and follow along and feel free to mute me. So you can just check in once in a while and see if we're still in the notebook. Okay, so this is the notebook about belt state. So the first part here again, if you were in my breakout room earlier, you heard me say this, but those who didn't, the first part is always to import all the content from the package. So we will run this cell here and I'll just click the button so you can see what I'm doing. And so there's the star that I was talking about. This is the part that always takes the longest when it's loading all the package. So once this is done, then the rest can keep going. And so for this example, we now want a content memory that has 2 memory positions. In the old example, we already saw that we can tell the content memory how many positions it wants through this position number here. So we set this to 2 right here. And so we'll run this part. And now we have the content memory ready to go and we'll reference it by Q memory 2. Next, we need to initialize those 2 qubits. So we initialize a qubit in slot 0, that's position 0 right here, and initialize a qubit in slot 1, so that's right there, position 1. So let's do this. And there is no output because there's nothing coming out. It's not complaining, that's good. And now comes my favorite part, the not physical part. See, that's where you can tell that I'm not an experimentalist. I guess I'm perfectly happy to doing something completely not feasible. We'll peek at the qubit and we'll check the state. We'll know exactly which state the qubit is in. Even if it's a superposition state, we don't have to look at a measurement result. So first here, we peek at the qubit in slot 0. And then we peek at the qubit in slot number 1, and we reference those peekings so we can print the state. So we're printing the state as a cat state, which will come out as a vector, giving us these amplitudes. So we can see here, both of those are this vector, the 1, 0 vector, which means those 2 qubits are in a 0 state, just like we expected them to be. Now we want to apply the Hadamard gate to qubit 1 so that we can create a superposition for the qubit in slot 0 and then peek at the state of the qubit again. So here's the instruction that applies the Hadamard gate. And with the 0 here, that's how we can tell that we're applying it to the qubit in slot 0. And then we'll print out the state again. Let's run this. So here's our state. And now you can see this is actually this vector here, 1 over square root of 2. And it has both a coefficient for the 0 and a coefficient for the 1 state. So it's this superposition state right there. And now we'll go ahead and we'll apply the CNOT gate with qubit 1 as a control and qubit 2 as a target. So when qubit 1 is in a 1 state, then qubit 2 will have a NOT gate applied. And what we will find is because we're entangling these qubits, their state will now look differently in that split. So you can see here, that's not a 2-dimensional vector anymore. Now it's a 4-dimensional vector. And so that's because now it's in the basis of a 2-qubit system. And the state now looks like this. So we have 1, 0, 0, 1 with the prefactor. And so this is an entangled qubit state. That's a belt state. And I know multiple short courses have talked about this, but basically, if you would measure one of the qubits, let's say you measure qubit 1, which would be the first number in this 2-qubit state, and you find a 0, then your second qubit, when you measure it, will also give you a 0. They're correlated here. And so let's try this out. So we'll measure the qubit in slot 0, and this time we got a 1. And if we now peek at the state of the qubit number 2, we'll see that because we measured 1 qubit out, it's not the state of a 2-qubit system anymore. We'll go back to having a state of a 1-qubit system. So we should have a 2-dimensional vector. We do. There it is. And so this qubit is now in the 1 state, which makes sense because if we measure a qubit in a 1 state, it will give us 1, which is exactly what the other qubit gave us. And now we can do this here. There. And there's our measurement result. So we would originally have you now spend some time in the breakout room. We have a message. It's NetSquid deterministic. So NetSquid, we think how NetSquid is doing everything. So I think from what I remember and how they're determining what is happening is when you have a superposition And they actually, for the measurement results, you can also give the probability of getting the result. So it would give you the probabilities of getting both results, and then it randomly, in accordance with the probabilities of getting one, it will assign you one of those results. So it's a pretty good simulation. Are we still, there's still someone in the waiting room, so I just admitted them. I don't know how that's going to go, but okay. So I don't know. I mean, I have most people in this room. I don't know if there's anyone in a breakout room. It doesn't look like it.
Yeah, no, I think
Oh no,
everyone,
there's some people in. Oh no, they're not in. They were
yeah,
just in.
everyone is in the main room right now.
Okay. So I am just going to be functioning under the assumption that it's not working, that people are really working on the server on their own. Is that correct, Jaime?
Yeah, there are some people who are saying it's just really slow. And so they just kind of save the files, I think.
Okay. All right. So I'm just going to go ahead and work through the examples then. So we will. So if you come back and if you have NetSquid, or what we can also do, maybe for a week or so, we can leave the server running.
Yeah, that can
Give
also
people
work out.
access. So this was only supposed to be for today, but since it wasn't working, since we had too many people for this little server that we used for this, we'll just give you a week to try those out on your own. So we'll do it like that. So that will hopefully be a good compromise. So now I'm just going to keep jumping back and forth between my two slide options here. Where's my talk? Here's my talk. Okay, share. There we go. So this was number C. So now let's look at notebook D, quantum memory example 3. So now the fun starts. So we're still in a relatively simple scenario that we just have 3 qubits. And we haven't even talked about if they're in a node or where those qubits are. They're just, we can just store them in a memory. But we're still trying to use what we have learned so far to teleporting a state from qubit 1 to qubit 3. So that's really the main purpose of this notebook. And so what we will do here, we will first place our 3 qubits in the quantum memory. Then we will entangle the 2 qubits. So we will basically apply these 2 gates to these 2 qubits here. We'll perform the belt state measurement. So this means we'll first apply the C0 ahead of Martin and measure both of these qubits. And then we'll have in the code that depending on the outcomes of these measurements, the Z or the X gate are being applied to this last qubit. And then finally check the state and calculate the fidelity and see how this actually worked. Like, did this all work the way we wanted it to? Oh yeah, and I just got a question in the chat. Yes, I did skip over the exercise. Main reason for this being, I think this is really, so the practice you mean in the bottom, right? This was really something we wanted you to do on your own. So type the things into the notebook. And so we will just not do this live, because since there are too many people who I think won't be able to do it on their computer or on the server at the moment, I'm just going to work through the notebooks and we will give you access to our server for a week or so. So you can come back when it's not so overloaded and then do this on your own. It's maybe better anyways, because we probably didn't give enough time for everyone to do all those practices. But we wanted to have a variety of levels too, so that somebody there, if you're new, you might just work through the notebook. If you know what you're doing, you might want to do all of the practice suggestions. So for today, we're just going to improvise and we'll go through the notebooks together, and the practice we leave for you afterwards if you want to, and you can access the server then. And if it's not so many people, it'll be fine. Okay, so that was notebook D. So now let me go back to if I wouldn't use it all the time, here's my Python. Okay, so that was example number 2. So I'll close this and I'll shut it down. So now I'm opening D. Okay, so the teleportation circuit. So this is what we want to do, right? So we have these 3 qubits. We want to apply all of these gates and the measurements and then see if we really manage to get the smiley face from qubit 1 to qubit 3. So the usual, we will first import the content of the NetSquid files. And now we want to have a memory with 3 memory positions. So we will need to set here the number positions to 3. And then right away, we will initialize the 3 qubits. So this is initializing qubit, a qubit in slot 0, slot 1, and slot 2. Next, we will again cheat and peek at the memories and see if the qubits are really there, and also look at the states. And I forgot to actually evaluate this. Here we go. Okay, now we have the memory. And they are the 3 states. So you can see each of these memory slots has now 1 qubit, and each qubit is in the 1 state, in the 0 state, the default state. So this is the part that's right here. Now what we want to do is we want to set the state of qubit 1 to something a little bit more interesting, because what would be the point of teleporting a 0 state? Qubit 3 is already in a 0 state. So normally we wouldn't want to know what state we're teleporting, because then we can just create it over there. But since we're simulating it, we're just setting this state. We're going to say we're going to go with this superposition state, the 0y state. And our goal will be to create this state at qubit number 3 just by running through this teleportation circuit. Okay, so first comes the part where we create the state. So that's not in the circuit, right? Because that's basically making this smiley face here. So there we go. So let's run these 2. And now we can see this qubit is really in the state we wanted, because this is the vector for having 1 over square root and 1 over square root I right there. And the state is also predefined in NetSquid, so we could have also just used it, but we really want to practice applying gates and creating the states. So if we show this one, that's the exact state we were trying to make. Next, we entangle the qubits 2 and 3. So we're generating this entangled pair that we need to teleport. So this comes here. And then we check what the state looks like now. And so this is a good example to see how the states are changing. So before we entangled those 2 qubits, every qubit was in a single particle state, right? But now the first qubit is still in a single particle state, but because we entangled qubit 2 and qubit 3, they are now in a 2-particle state. This is why we have a 2-dimensional vector here and a 4-dimensional vector over there. So qubit 1 is still in the state 0y, that's the one we want to teleport, and qubit 2 and qubit 3 are now in the spelled state. And now comes the part where if the qubits were physically separated, we would just act on the 2 qubits that are with us, the people who want to teleport the state. So we're doing the spelled state measurements on the qubits in slot 0 and slot 1, so up here. So this is the part that we're working on now. So we're trying to do a belt state measurement so that the outcomes of these measurements will tell us what to do to this qubit without knowing what state we're trying to teleport. Here we go. So let's run this part. And then we measure the 2 qubits. Here we go. See, when the computer is cooperating, it takes no time at all to run it on the server. So maybe try it once in a while. Maybe the more people stop, then there'll be some server for some others. So depending on the measurement outcome, we now perform the corrections. So if the measurement of the qubit in slot 0 gave us a 1, then we have to apply the X gate to this qubit that we're trying to teleport to. And if it results, if the qubit in, oops, that's not right. But the good thing is I can correct this on the fly. So this should be a slot 1. And so there we go. Oh, that's funny. Oh no, it must have been right. I must have just looked wrong. There we go. So if the qubit in slot 1 gives a 1, we apply the X gate. If the qubit in slot 0 gives a 1, we apply the Z gate. So there might be cases where we have to apply both gates. There might be a case where we just have to apply one gate or the other or no gate. And so this is the part where we do this. So here's our conditional. If this measurement results as a 1, then we correct. And if this one is a 1, we correct this way. And we can see in this case that we're running right now, we actually had to correct with both of those gates. And this means the qubit is now in the state that hopefully is the state that we were intending for it to have. This is the state. It looks a little bit uglier because there is a little bit of error from just numerical problems, tiny rounding errors. And if we now want to see if this state that we have in qubit 2 is actually the state we wanted to teleport, we can look at the fidelity. So the fidelity is a good measure for us to see how well a state actually agrees with the state that we wanted it to have. So here we wanted to teleport this Y0 state. So let's see how the fidelity looks. And it's really, really nice. So that would be the teleportation circuit. And then when you come back on your own later on, hopefully, if you're interested, go back and try to teleport some other states. So in our example, we teleported this Y0 state here. Change the code and so modify it so that instead of teleporting this case, you would be teleport this state over here, this plus state, or maybe the Y1 state. And just keep in mind that when you're doing this and you're calculating the fidelity, you also have to go back then here and change the target state, right? So if you're teleporting, for example, the plus state and you're trying to calculate the fidelity and you're comparing it to Y0 state, that's not going to be very good. I'm just going to keep admitting people when they come. All right, any questions? I don't see anything. I don't know, Jaime, if you're working on questions.
Yeah, I'm answering the questions on the side.
Okay.
If
I don't
anyone
even
has
see
them,
any.
feel free to ask me and I'll answer them.
Okay, so should I just keep going?
Yeah.
This was the last. Okay, what we're going to do is let's take a 5-minute break, or actually 7-minute break, and we'll come back at 10:30 and we'll go into the next chunk of examples. Okay, looks like some people teleported. Awesome. Okay, and then somebody just downloaded NetSquid on the fly. That's great. If you have it installed, you should be able to just run our notebooks and just work along with it. And if you have other questions, I can try to come back to you later. And then somebody else missed the username. So Jaime, I don't know if you have assigned a username to Mengyun yet.
I believe I did. I will check
Or
right
maybe
now.
just give him a new one. Or
Yeah, I
something.
might just give a new one.
Yeah. Okay, and then so Mengyun, since I don't know how much you heard, but the saver is not quite living up to our expectations. So be patient with it. You might have to just follow along and come back later. But we will leave this server open for a week or so people can come back and do the practice on their own. All right, so let's go back to, where is my screen? Oh, there we go. That's what I'm sharing. Okay, so where are we now? Here. So this is what we wanted to do, right? We wanted to see if we can teleport a state from qubit 1 to qubit 3. And we talked about what we needed and we did this. So that's great. There is a problem though. So it's not a good idea to get so excited yet, even though I think first time I did it, I was like, yay, it works. It was awesome. But that was very abstract. So we just applied gates. We could have done the same thing really in Mathematica or something like this. Not saying that you can't do a lot in Mathematica anyways, but we didn't really look at the physical system at all. So when we applied a gate, we just instantaneously changed the state. Just multiply a matrix to a vector and this a new vector. So what we wanted to do now next is we want to see like what ways does NetSquid offer, and most simulators will have similar ways to make this all a little bit more physical and to maybe target a particular hardware where you know a certain gate will have errors or a certain gate will take X nanoseconds to run, or you will only be able to, for example, measure on one of your memory slots, but not all of them. And this is where we're now coming to the quantum processor. So the quantum processor, that's really our way how we can have a quantum memory, and the instructions have physical components. So we can say, how long does it take to apply this gate? What errors will happen or might happen? What are the odds of having a certain error? What restrictions do we have? What topology? And so this is where we're going to go next. So we have here our quantum memory with our positions, and now the new part is to have these physical instructions. And because now these gates, for example, applying a gate will come with a certain time to apply this gate, this is where we really have to start using the discrete event simulator. So I'll talk about this when we come to the notebook now. So I'm going to go back. So for those of you who missed this part, since the server isn't quite up to handling everybody at once, I'm going to go through the notebooks live. I won't do the practice part at the bottom. I'll leave this for you to come back to, but we'll at least go through everything together. And you're always welcome to try in between and see how the server is handling your things. So let me share to my, so this is number E, example 1. So if you are looking along, and if you just want to open the notebooks and your personal, an Emacs or something, you should open fine too, or a text editor. I actually don't know how this would look in a text editor. So this is our notebook this time. So here is what we're going to practice. We will take into account the physical duration of the process, we'll include potential errors. Those actually come later on. And the big part is we will start using discrete event simulation. So like I said in the beginning, NetSquid uses a discrete event simulator, which means that the system changes because of a discrete sequence of events in time. And each event occurs at a specific time and then changes the state of the system. And between events, the system is assumed not to change. But you can still say, for example, an event could be, I'm transporting something through a channel, and this will take so many nanoseconds. So once I have transported, the system would then have progressed by so many nanoseconds. And if there are any time-dependent quantities, like maybe at the phasing rate, like at the phasing model, error model, then this would affect how likely you are to have a problem. So our usual, first we will load all the packages. That's the longest part. And then check if I'm missing anything. I don't think so. I don't think I have any new comments. Okay, perfect. And it should be loaded in a second. So in this last notebook, we learned how to create a quantum memory, right? With these preset positions for storing them. But our instructions were not physical. Everything was instantaneously, no errors. So now we will change this. We will switch over to having a quantum processor. And a quantum processor will come with a specific set of physical instructions. And that's really the cool part. So if you are interested in modeling very specific hardware and you know the gate times, you know the problems, then you would model this by changing how these instructions are being run. And then if you want to model a different system, or you want to see like, how does everything change if my gate is now so much faster, you can just change these physical instructions and then you can model it this way. So as our first example, we will look at 3 physical instructions. Initializing the qubit now takes 3 nanoseconds. And if you're wondering about any of the numbers I'm using, I'm just following what NetSquid did in their examples. So they went this 3 nanoseconds. I figured I'll go with 3 nanoseconds for these here too. So we'll say initializing takes 3 nanoseconds, applying the Hadamard gate takes 1 nanosecond, and the X gate also 1 nanosecond. And now we will use this quantum processor. So here's the function for this. And the big part first is, this is how we tell the quantum processor, or this is how we define how our instructions are looking. So here we have the initializing a qubit, and this is the time. So there are 3 nanoseconds. If we want to apply an H gate, it will take 1 nanosecond. So this is the structure for this. And now we initialize the quantum processor with the quantum memory. So, oh, those were the instructions. There's the processor, sorry. We create this quantum processor with 1 slot. So this is similar to the memory earlier. Number of positions is equal to 1. And then this is different. We now tell it what physical instructions to use. So the quantum memory was just having non-physical ones. We could tell the quantum processor too to fall back to those. We can do that. But it's a good idea to just define your own instructions there. So let me run these 2. And now, like I said, this NetSquid uses discrete event simulation. So now that we have time progressing in our system, we have to include this. So we can check our current time just like this. Simulation time, we haven't done anything, so our time is 0. And now every time we are executing an instruction, this will advance the time. So if initializing takes 3 nanoseconds and we initialize a qubit, then afterwards it has to be 3 nanoseconds until we do something else. So let's do this one here. So we are initializing and then we're running this event. So just writing the coprocessor execute, that just means we're scheduling that this event should happen, but we haven't actually done it yet. It will not happen until we actually run the simulation. So process the next event. And then if we check the time, we see, yeah, 3 nanoseconds, sorry. So next we schedule the Hadamard gate. So we want to apply the Hadamard gate to our qubit. And we remember from above that this is supposed to take 1 nanosecond. So let's run this one. And then we check the time, and yes, so it went from 3 nanoseconds to 4 nanoseconds. And we can still peek at the state of the qubit exactly the same way as we were doing it for the quantum memory. The only difference is instead of saying quantum memory 1, we now have quantum processor 1. So this was the name for our processor. And then we can still check our state. There we go. So here is something, and that's the first time we've had a red box. if you're playing on your own, you will run into problems, right? So a common one would be that you're trying to apply a gate that you didn't actually provide a physical instruction for. So if we go up here to our physical instructions, we defined only initializing a qubit, applying the header mart gate, and applying the X gate. What if you want to measure? What if you want to apply the Y gate? Those are not defined here. You could set it so that the default is when the instruction is not there, it just uses a non-physical instruction, so without time or without arrows. But it's probably a better idea to not do this, because most likely you didn't mean to not have an instruction, you just forgot. And so whenever you're trying to execute an instruction that cannot be matched to a physical instruction, you'll get an error. So here I'm going to try to apply a Z gate, which I did not provide. And so I'm getting this, right? Missing instruction error, missing physical instruction for the Z gate. So if I want to fix this, what I need to do is I need to go back to my physical instructions, where I only initialized the qubit, applied the Hadamard, and applied the X gate. And I need to add the Z gate to this right here. Oh, that's funny. And that's the end of my color block. I think I'm going to maybe do this like, it's fine. There we go. This will work. Okay, so this is really everything to this notebook. And then the practice suggestion for you would be to go back and mess with it. So change how long something takes. For example, change it so it takes 5 nanoseconds, apply different gates, and run through all of these steps and just kind of get comfortable with running the simulator. So this was that. And I'm going to shut it down already. It's fine. And we'll go to the next one in a second, but before, let me go to those transition slides. There we go. Okay, so this was number E. Oops. Oh yeah, here we go to F. So our next one that we will open, and please feel free to put in the chat if I'm going too fast or too slow. It's a little harder to judge now, since those were all meant to be work on it for a little while.
Inez, someone commented, maybe in the next example, just give a little recap on some of the things that you covered. So like the gates, why you used them. Like early on, you talked about how you use certain gates to do certain processes. Maybe just give a recap on why you're choosing these gates, whether it be for entanglement or.
Oh, so maybe go back to something like this here. Okay.
Yes.
And this example will actually come back. So yeah, so keep in mind what you're trying to do, and you will want to do different things, right? So the example that we are using here to practice and try all of this out is just a very common one, because teleportation is so important for so many aspects of a quantum network. And so our toy model is just teleporting a state from one qubit to another qubit without them being physically separated or anything like this. And it relies on different parts. And in other situations too, they will have very similar things. So oftentimes you will try to entangle qubits by applying gates to them. And this is what is done in this box here. So you have a qubit that's originally in the 0 state. So that's not a superposition state, just a 0 state. When you're applying a Hadamard gate to it, it makes it into a superposition state. So that's a very quantum thing now, right? Because not that you can't have superpositions otherwise, but now you're getting this uncertainty of when you're measuring, are you going to get a 0 or 1? So the Hadamard will give you the superposition part. And then the control not gate, that one will effectively link these two qubits together. Now let me go back and see where I had the state. I think it must have been in my notebook. But so I'll stay on this one. So in this case, applying the Hadamard and then the control node to these two gates, and actually trying to, oh yeah, I can do this one. I don't want to hook up my iPad right now, but I can. That was not it. What happened now? Oh yeah, now I have to, I was trying to draw, but then I first changed my slide first. There we go. So now let me try to draw again. I'll just write this. This one, I think. Okay, nope, that was the wrong part. somebody I know actually teaches with Annotate. I don't think I would be capable of doing this. I usually would use, let's see if this works. An iPad, perfect, there we go. So if I do this, the state for these 2 qubits, that was when the wrong lines, these lines. There we go. The outcoming state would be, oh boy. Would be a state where the outcomes of the measurements of the 2 qubits are not correlated. So if I'm measuring my qubit, my first qubit, which is the first position in this cat state. So the cat state, this is the description for having a 2 qubit system. If I'm measuring and my outcome of my measurement result is a 0, then I know that the system had to collapse in this state, which means my other qubit is also going to give me a 0 as my measurement result. So this is the entangling part. And then the BSM part, that's a belt state measurement, that's fairly commonly done. And it just means you're basically executing the steps to entangle two qubits to create a belt state backwards. So you apply the control knot, apply the Hadamard, and then then measure both qubits. And then in this last part here, this indicates that the outcome of your measurement will then be used to decide which gate you're applying next. So I'm not really sure if that's what the question was targeting, but I'll try to also, when I go over the notebook, to get rid of those annotate things again. Clear. There you go. Cover again the gates too. Okay, hopefully that helped a little bit. So which one were we at? F? Yeah, F. Okay, so our next one is topology. So now we want to use the quantum processor and use these physical instructions, but also to put in there that we can use them to dictate or to specify what we can actually do for a specific qubit. And not that it matters which qubit it is, just matters where the qubit is stored, right? There might be a case where you can measure a qubit that's stored in a certain position, but you can't apply an Hadamard gate to it. And so let's go and do this one. Oops, I have one more. Forgot my next slide. There we go. This is the summary of this that's supposed to help you to get prepared for what's coming next. So we'll have the quantum processor. The topology is new. We'll still practice some more how to use discrete event simulation and how to operate on qubits in the quantum processor. And so what I mean with topology is, so let's say you have a quantum memory with 3 positions, position 0, position 1, position 2. You could define that on position 0, so any qubit that's stored in here, you could apply a Hadamard gate, so create a superposition in the next gate. And maybe you could have a control NOT gate for the qubit in 0 and 1, but you couldn't have a control NOT gate for these 2 qubits that are stored over here or over there. Or you could only measure the qubit in position 2. So those are all things we can now define with topology. Yeah, okay. So this was F. So if you're following along in your own notebooks, this would be the F part. Okay, so at first our usual, this is the part where we're importing all of the Let's Good functions and classes that we're using. And so you might have noticed if you compared what we've loaded in previous notebooks and what's new in the quantum processor, this is the discrete simulation engine. Okay, so now comes the part where we are adding where we can do something. And this is how we do this. So we give a topology, and that says which qubit in your processor this can be run on. And that's why it's going to be important that your processor and your instructions match. So if I, for example, have a processor that has only 1 position, and then my instructions don't use like more or vice versa, and it's not matching, you might run into problems there. So we want to have instructions that can actually work on all of the positions we have, or not much. Yes. So we will define here a toy case where we'll have the Hadamard gate that we can apply on the qubits in slot 0 and 1. And the X gate can only be applied in the qubit in slot 1, and the control NOT gate can only be applied where qubit 0 is the control and 1 is the target. So if I wanted to apply it the other way around, it would complain, right? Because this is how I said it can only work here. And then we have also something else that's parallel. So this basically just tells you, can you apply these gates at the same time? For example, if you have different qubits, is there a problem if you're trying to do certain things at the same time? And so we can say for which of those we want to allow this or not allow them. So let me run this one. And then the processor. So here's our processor. We're giving it 2 positions, and here's where we're calling these instructions we applied up there. Now, just to practice using this simulation, we'll check the time. What's the difference? Actually, I have a question in the chat. What's the difference between topology and positions? So topology just describes what you can do on which of these positions. So picture your memory as a big box, and it has like these little containers where you can put your qubits and you give them numbers, and you want to define what you can do to certain qubits. That's where the topology would come into play, at least in this context. So this is the way how you would tell your processor what it can do to qubits that are stored at certain locations. Hopefully that helps. And there's someone else. People just keep coming back and forth. So we check the time because we're starting a new notebook. The time is 0 again. So now we initialize our 2 qubits. And again, remember, this executing just means that we're actually just scheduling this event. We have to run the event for it to actually happen. And like before, initializing qubits takes 3 seconds. Something else that is new that you might have noticed here, there's a 0, 1. So we're actually here initializing both of the qubits at once. Then we apply the Hadamard gate to qubit number 1. Qubit number 1 is in slot 0. And that takes a second, the Hadamard gate. We apply the control NOT gate, where the qubit in slot 0 here is the control, and the qubit in slot 1 is the target. And then, I guess I didn't run this yet. And now we're at 5 seconds. And now last, let's peek at the qubits that are stored in here and check their states. Here are those. So you can see we have effectively entangled these qubits, and you can tell this from the fact that you now have a 2-qubit system. So when you're interacting, it doesn't mean they have to be entangled, but we interacted the qubits so that now we are looking at them at a 2-qubit system. And so they're in a shared state. And in this case, we did create the spelled state that we had in the protocol earlier. And so to come back to what I was talking about earlier with the gates and what they do, maybe this would be a good moment to come back to this since there was this question. So the Hadamard gate really put this first qubit in a superposition where it has, when you're measuring, you have the probability of finding it in either state 0 or state 1. And then the control NOT gate then completes the entangling operation, because depending on what the outcome of your measurement or what state your qubit is in, something else would happen to the other qubit. And so this is how the qubit ends up in the state right here, where you can see if you're measuring something and your qubit is going to collapse, they're always correlated. If qubit 1 gives you a 0 as your measurement outcome, the other qubit will too. And if you end up measuring a 1 for qubit 1, then you will measure a 1 for qubit 2. That's the really cool part of entanglement. So practice suggestions for this one, we were suggesting to just practicing entangling qubits in different belt states and using these physical instructions. And just keeping in mind that if you are needing gates that you haven't defined in your physical instructions, you have to include them. You can't, if your instructions don't have a Y gate, you can't apply a Y gate until you add this into the instructions. Okay, so this was that one. So it was F. Then we have one more quantum processor one. So let me close this one. I'll go back to my transition slides. Oops. There we go. Yeah. Okay, number 3. And then when we're done with this one, we'll take a quick break again. So we can go in these chunks. I think we're actually pretty good in time, so we should be fine. So the last example for the quantum programs. So what we're doing here for the quantum processor, we will talk about quantum programs. So they are really useful. So far, you've noticed we've been very cumbersome. We've been applying every instruction one by one. So we would say we're initializing, we run the simulator, we apply the gate, we run the simulator. That's not really how you would want to do this, right? You would actually want to have a program that would run on a processor where you can have all these steps already scheduled, and then you just run this one program. And that's what we're going to focus on next. And so we will rewrite this teleportation circuit that we already worked on, but this time we'll use a program. So instead of submitting every instruction separately, we will have this one little program that will run on the processor. And that's it, taking all of this together. So here's our circuit again. So this is what we're going to do. We'll have the steps where we are first creating the smiley. So we'll set the state of qubit 1 to something funner. I think we use the why not state again. Then we'll entangle these other 2 qubits. We'll do a belt state measurement on these upper 2 qubits, and then use the outcomes of these results to manipulate qubit 3 so that afterwards this qubit is in the smiley face. Okay. And this should be G. Okay. So we go first, the usual, we load all the net squid parts. And while this loads, I'm just going to check if there's anything. Isn't the smiley already? Okay, so Bob has a question. Why we're doing the top Hadamard gate, isn't the smiley already in a superposition? I will come back to this when I have the diagram open. I think it's easier to explain it then, and I don't think I have it in this notebook. So, oh, there it is, perfect. Let me go through this. So the point of the teleportation is what you're doing here is not supposed to matter what state your smiley face is in. I made this into a superposition, one of the superposition states, but it's supposed to work no matter what state it is. If it would be a 0 state, of course, it would be pointless, or 1 state. So the idea is that this is a state that is just any possible state. And then by going through these motions, no matter what the state was, because of the way you're using the entangled state here, entangled qubits here, and you're doing this belt state measurement here, this qubit in a sense you could say recreates itself, right? So the state that this qubit was in will then be the state that the last qubit will be in afterwards. And it will work no matter for what state your smiley state was. So I don't know if that helps, but basically what you're doing is by doing this belt state measurement, which you need this, I think that's the top Hadamard gate you're talking about, and you're talking about this one. You need this kind of process to figure out information about this qubit. And that's why you're applying this. So hopefully that will answer the question. So in the meantime, this finished loading. So let's work on these quantum programs. And so there again, my red arrow boxes. This is something that if you would have tried stuff out on your own, you might have noticed this. So let me initialize really quickly the instructions and the processor from one of the previous examples, and then I'll show what I mean. So in this example, we had a initializing Hadamard gate, X game, and a quantum processor. And now if you would do something where you're trying to schedule multiple gates or multiple events at once, so in this case, an X gate and a Hadamard gate, and then you're running it right away, what you would get is a busy error. So the problem is that you're trying to execute the instruction for the Hadamard gate, but your X gate hadn't actually finished yet, because this one took a nanosecond and you're trying to more or less put them in the queue at the same time, so that you can't do this. A workaround would be that you could run each of these events sequentially. So you could, first let me reset the processors, so it gets rid of the error messages. So I'm resetting my processors and my simulation time. So what I could do is I could schedule my initializing of the qubits and then run this event, and then schedule the X instruction of the X gate and then run this event, and then schedule next that I want to apply Hadamard and run this event. And this will work. Whoops, there it is. So that will work. But if I try to do 2 of these within one execution, within one run event, it doesn't work if they're interfering with each other. So if one hasn't completed yet. Okay, so the idea here is that instead of doing this, we use quantum programs. So we just write one program and then we just run this program on the processor. And here are all the steps. So remember, if this is going too fast right now, you have these notebooks, you can always come back, you can log into the server during the week and you can do this in a little bit more time. But in detail, the steps we're going through here. Oops, that's wrong. That's not what I meant to say. Okay. There we go. This is not even. Oh no, never mind. That was right. Ah, great. How is fidelity calculated? I will come back to this. Let me just fix my. Where's the unbutton? There we go. Okay, perfect. I don't know what I was seeing. Okay, so here we go. So we initialize the 3 qubits, and I will come to fidelity in a minute, David. So David was asking about how fidelity is being calculated. So our first step is the quantum program should initialize all 3 qubits. Then we want to set the state of the qubit here. So we want to make the state into the smiley face, and we've been using the state the whole time, so we'll do the same. Then we'll do, and this was supposed to be entangle. Okay. Then we will entangle qubit 2 and qubit 3 in this belt state. First applying the heteromer, then the C0. We want to perform the belt state measurement on these upper 2 qubits and then apply the additional correction. So all of this is supposed to be part of this quantum program now. But instead of executing all of them, we will now go back and we will have a teleportation program for this. So here is the language for a teleportation program. And as you can see here, this is the program. And it's actually everything we did before, just all put in one program, right? So the first thing here is we need to know the indices of the qubits so that the program will know what qubits it's actually talking to. Then we initialize the qubits. And so now we reference the indices we were getting here. We set the state of the first qubit to this targeted smiley face that we want to teleport. We entangled qubit 2 and qubit 3. So those are all the same things. And this is supposed to do a BSM measurement. And then we're doing a belt state measurement. And then afterwards, we run all of these instructions. And that's because this all has to have happened before we then can apply the corrections, right? So we have to measure, and the outcome of the measurement, we have to store this so that we know what the outcome was, so that then we can go back and say, okay, if we measured a 1 for qubit 0, we have to apply an X gate. If we measured a 1 for the second qubit, then we have to apply a Z gate. So let me run this one. So there's the teleport program. And now in order to do this, we only execute this one program. But of course, first we have to give the instruction and define the processor. So now we have a lot more instructions than before. So these are all the instructions we want to have for this example. And then I'm resetting this since we had this other thing in there. And then we are initializing a quantum processor that has 3 slots here, and then uses all these instructions up there. And now all we have to do to run all of it is we just schedule to run the teleportation program. And then we just run the simulation one single time. And we can see that it advanced by 15 nanoseconds because we had all these steps up here that we were going through. There. And now comes the fidelity. So to look at the teleportation, we look at the fidelity, and the way it was calculated here, I think is the squared fidelity. So it's basically comparing the 2 states with each other. So it's a state fidelity. I would have to go back exactly how they were calculating it. But the NetSquid documentation is actually really good. So you could go back into the function and look into the code. Not everything in NetSquid is open code. They have some part that's behind the wall, which isn't ideal, but they give enough open source or enough access to their codes to at least figure out roughly what you're doing. So that's pretty decent. So let me run this one here. And the fidelity for this one was also excellent. Okay, and so the practice suggestions for this example here would be that we would write a new teleportation program that instead of like before, just teleports different states. But in this case, using a quantum program and using physical instructions. So that would be the challenge for this. And with this, so let me see. Let me go back to the slides. Okay, yeah, so we're coming to channels are coming next. Okay, I would say let's take a 7-minute break or 15-minute break. Let's go to 11:15. So I'll put this in the chat for everyone. We will come back at 11:15 local time. So it gives you a minute to go back and look at the outputs, and then we'll attack the next chunk, which will work with channels. So how we will have nodes, and instead of talking about a memory and a processor, and we'll actually talk about connecting nodes to each other. So we'll move away from this abstract teleportation program where everything happens at one memory, but really going to the point where we have a person who wants to teleport a qubit to another person who is far away. And so they have to be connected over a quantum network. So we'll come to this one next. And in the meantime, hopefully we'll get a chance to follow up with whatever questions are outstanding. One real quick one, because I see it before, is there a reason why it's in nanoseconds? So NetSquid overall has their default instructions more targeted towards diamond and vacancies, but that's just what they had preset. They give you freedom, I think, to rewrite, I think, what you want to have. No, I don't think so, but you can just change the timing. So nanoseconds was their default, as far as I know. Okay, so we will be back in now 6 minutes. And see what I'm missing. So I still had one question in the chat, and the question was why I had said we're running on a quantum processor and we have model errors, but the fidelity is unchanged. And so, good point. We actually didn't include any errors yet. We just started working with the system or the functions or the class that allow us to do that, but we haven't done it. So far, all we have said is the gates take a certain amount of time. They can only run on certain slots, but the part where we would include errors or error models, we haven't actually. Oops, I forgot to post that I was going to be back at 11:15. I think I meant 11:10 anyways. Did I say 11:15, Jaime? I think I might.
You might have said 11:15.
Yeah, so maybe we should wait. But anyway, so that's the reason why. So let me go back here then. I'll talk a little bit about this while we're waiting. So all we have done here so far is saying how long the gates take and where they can run and the instructions in general. We haven't really included any errors yet. So that's why. But even once we do, we still sometimes might get the perfect fidelity because that's the whole thing, right? It's probabilistic. It might happen, it might not. And we will see that later on. Okay, so I'll give it another 4 minutes. All right, so before we start back up, let me just answer the question in the chat, or there was one in the Q&A too. So there's a question in the Q&A. Can you peek in the code within the program if you want to look at qubit 0 before the measurement, the processor is declared afterwards? So I'm trying to remember, and I don't have all of my notebooks open right now. You can peek in what we're going to introduce next, which is inside the node protocol. I don't think you can peek inside the program. You can peek after you run the program. When you declare the processor, I mean, so the declaring the processor is a little bit different because nothing, you can work on your program and you can try to peek in it, but your program will run on the processor. You have to declare your processor first anyways before your program can run. But from what I remember, and I would have to go back now, I don't really want to try it on the spot. Maybe Jaime knows. I don't think you can peek within the program. I think you can peek after you executed the program, but you can peek within a protocol, which we will cover next. Hopefully that will answer your question. And then we see there were a few more in the chat. For large simulations, can you break your total circuit into modules for limit and error to draw large circles? I think what you mean is if I can have multiple programs, and then is that what you mean? Maybe you can specify, but you could definitely, like if I don't think I'm sharing, what am I sharing right now? Oh, this one. So we defined one quantum program that runs all of it. We could definitely define programs that are just doing certain parts. That's actually what you would want to do, because a lot of times you would, let's say, always entangle, so you would want to have an entangle program. And so you just call this program whenever you want to entangle, you just tell it which which qubits to run on. So I'm not sure if this answers your question, so please feel free to come back. And then there's one more question, and I'm going to come back to this later. I'm going to try to come back when there is another break. Let me see one more here. Okay, I think that was it. Yes, okay, so, and there was the follow-up question, if you can do a module for Entangle BFM, yes. So you could have all these different programs. Okay, so let me come back, and then when the next break, I will come back to the other questions. So what have we done so far? We have first looked down here. So we had these 3 qubits we were teleporting, and we were teleporting first like very non-physical, and then we made it a little bit more physical by having topologies and duration times, and we could have included errors, we just didn't yet. So we're going to consider this part kind of as done, but the upper part here, that's really the part that we should be more interested in, because that's what we would need a quantum network for, and what we also, it's kind of this double thing, right? We need this for a quantum network, and we need a quantum network to do it. So now let's work on networks. So we will now look at a scenario where we still have the qubits, and we would start out with having 3 qubits together at one node. That's our agent A. And then we still want to teleport the state of the smiley qubit to the agent B. But in this scenario, what we will do is we will entangle these 2 qubits, send one of them through a quantum channel over here, and then do the rest of the program where we do our belt state measurement, and then use the results to manipulate this qubit. The results will come through the classical channel so that we can teleport. So what we need for this, if we want to simulate is, we will need everything we've done so far. That's all we've done it. We'll also need to learn about quantum channels and classical channels, and we'll learn about connections, which is one way how we can connect the nodes without just connecting directly to a channel, and we'll learn about node protocols. So those are all the big items of the quantum channel modules. The first one is number H, quantum channels example 1. And so in this one, we'll start simple. We'll practice how to connect nodes to each other so that we can send qubits between nodes. So we want to have a quantum channel going from one node to the other. And this means we don't want to work with just a quantum processor anymore, but we want to move over to the class of nodes where a node then has a quantum processor. But what's new, and I think I have a picture a little bit, what is new is that, so this basically in here would be the quantum processor or the quantum memory. We want to have ports so that we can have a way to exchange information. So the node comes with these really convenient features to have input and output ports, and the channel can have input and output ports. And so this way we could have a qubit, and we can do something on a memory position and pop it out of the memory and put it from the memory output port to the node output port. And then from here, it can go into the quantum channel, it can go through the quantum channel, and then it can go into the node where it's supposed to go. So this is what we're going to look at now in notebook H. Share. It's amazing. I keep sharing between the same 2 windows, but they seem always to appear somewhere different. So every time I look, it's not where it was before. So this should be it. G, yes, okay, let me close this. And then H should be next. Quantum channel example 1. So let's go through those. Okay, so we will connect nodes. So first, you can see it's getting longer and longer. We're starting to use more and more things. So we're using now quantum processors and physical instructions, and we're using programs. And now is the first time we're using a node, and we'll use connections and channels and node protocols. So the features from NetSquid that we are relying on, the list becomes longer and longer. Okay, here we go. So our first example, so it will be kind of straightforward. We will just have 2 nodes connected by a quantum channel. And all we want to do is take a qubit and send it through the channel from node A to node B. Because we're using the quantum processor, we need our physical instructions. So what we're doing in this case is we're going to have 2 different quantum processors, and they will both go into a node. And then the physical instructions, we will use the same instructions for each processor. Let's do this one here. So first come the 2 processors. Each of them can store 1 qubit. And now we're assigning each processor to a node. And so the nodes will be physically separated from each other, right? And that's what we need the quantum channel for. So here are the 2 nodes, and this is the general structure for doing nodes. So node 1A and node 1B, we can give them names. Here we tell them how the memory and the processor are supposed to function. And this is the new part that's very convenient. Those are the port names. So this is how we can then tell the nodes where the information should go. And so Q in and Q out would be ports that allow us to transmit quantum information. Here we go. All right. So we initialize a quantum channel. That's the new part here. And the quantum channel, we will just use the NetSquid predefined quantum channel. Let's give it a name. And this is going to be our goal. And I know I'm falling behind on questions in the chat and the Q&A, and I will take another break soon when I'm going to let you look at something and I'll catch up there. So our goal is to initialize a qubit in slot 0 on node 1A. Then, oh, here's the picture, perfect. So we want to initialize a qubit here. Then we want to send the qubit through the channel to node 1B, store the qubit over here. And so what we need here is to connect the nodes are these ports and the channel. And the ports are a little bit tricky. They're really cool though. So we can put information in the output port of a memory position, and then we need to tell it where it goes from here, and we can connect them. So that's what these blue lines are. So we will do it so that whatever goes into the output port of this memory position will go straight into the output port of the node. They'll just get forwarded. And then from there, we can connect the output port of the node with the input port of the channel. And this one is not a forwarding, that's a connection. So technically we could go both ways here. We could go transmit information this way or that way. But there are different ways how we can do it too. We can also just forward, but we connect it in this example. And then we're connecting here, and then over here, whatever enters the node will go straight into the memory position for number 1. And there's all this part. So here, and I did everything right. Oops, I forgot to actually run the channel. Okay, there's the channel. So here comes the forwarding. So this is whatever comes out of this memory, and the labeling is that slot number 0 will have the output Q out 0. Slot number 1 will have the output Q out 1, and they also have inputs. Whatever comes out here will go into the output port of the node. And then over here, whatever that's on the other side, whatever comes into node B will go straight into the storage of the memory, straight into this position. And then the second part, that's where we're connecting the ports of the node through the channel. So here we can see we're connecting, so that's a two-way thing, but we're saying whatever comes out will be going to the send port of the channel, and whatever comes out of the, wait, the other way around, the receiving port. I feel like I did this backwards. Okay, then we initialize our qubit right here. Oh no, connect this way. And that's just a 3-second thing. We peek that there is a qubit, the qubit is there. So we're not using a program at this point because we're really going step by step up. We'll use a program right after this. And now next we want to send this qubit through the channel. So in order for this to work, it has to come out of the memory position, and that's where the pop function comes in. So pop just takes it out of the memory position, and then we can, whatever we took out there, we can then put into the output of the memory port. So this comes here. And now if we peek, we'll see, yay, there is nothing left in the memory. So the qubit is definitely disappeared from the memory. And then so remember, we wanted to get it from here to here. So let's peek into the memory on node B, and it's not there. So it's out of node A, but it hasn't come to node B. And the reason for this is that this channel action is actually another event. So for the qubit to go through the channel, we have to run the simulator again. And so if we do this took 3 seconds. Oh no, this took no time because we actually didn't give a physical length to the channel. But this would be another option where we can make this more physical. We can say how long the channel is. We can do like a fiber delay model and really take into account how long it would take for a photon, for example, to get through this channel. And now let's peek. And there it is. So this was the simple way of getting the qubit from one node to the other through a channel that was instantaneously fast. So we will make this more realistic. So I'll take a minute and work my way through those chat questions, and then we'll go to the next one. So let's see what we have here. So there is a question asking about, or more commenting that NetSquid might be useful for having multiple programs running and interacting with each other. I'm not positive, but I thought they were working a lot on this. I think it's actually pretty powerful. And then there's a comment on when you might be able to peek. That's the other good thing actually for having these notebooks. You can just try to peek. You'll see when it works. And then what do we have here? Does the simulator enforce the no cloning theorem, or can you send a qubit while also keeping it in memory? Oh, okay, good question. So yeah, this was in some of those courses too, right? You can't clone a qubit. What this means is you can't duplicate the unknown state of a qubit because you don't know what state it would be in. Of course, you can generate multiple qubits in a preset state. This is something different though. This is not even no cloning. If you have a qubit in your memory and you're trying to send it through a channel, you can't because it's in the memory. So that's this pop part here. In order for it to go into the channel, you have to take it out of the memory. And your question might actually have come before I got through this part. But so you need to take it out of the memory, and then it means it's not in the memory anymore. And then it can go through a channel. So hopefully this answered your question. Okay, is 100% of NetSquid functional available as open source? And no. So that was one of the reasons why we were considering not using NetSquid for this. It is not 100% open source. It has a lot of material that is accessible, but there are definitely some parts that they do not show. I think they might be open to working with people and sharing. I don't know how that works. I'm not involved in this. It is, however, such a convenient simulator in the sense of there's a lot of material on their website that is useful to just getting started really quickly. And a lot of functions are built in. And generally, I always prefer if something is completely open source, and Sequence is a completely open source simulator. That's also really awesome. We just felt that for this 3.5 hour situation, NetSquid was a good fit because you can do it's very easy to show how some of the things works because so much is already there. A lot of the other simulators don't have as much built in yet, but it's then great when they allow you to see everything, right? So Sequence, for example, is completely open source on GitHub. All right, so let me go back to, where did my slides go? Oh, there, okay, found them. Okay, so this was that one. So let's look at example number 2. So this will go really fast. It's very similar to the last one. We just have a classical channel instead of a quantum channel. So there are a few differences. So this time we're not sending a qubit, we're just sending classical bits. And to make it a little bit more challenging and practice some of the other things we've seen in the other notebooks, we then use a quantum program though, to come back to this. So let me go back and share back to this one. There we go. Okay, so this should be number I. Let me shut this down. And if you have questions, please feel free to also ask directly Jaime in the chat. I think he's doing a really good job in keeping up with whoever is checking with him. I am hit or miss. If it's something where I feel I can answer it right away because it's not a long question, I'll try to squeeze it in. If it's longer, then I'm not a good multitasker. I will have to come back for it in the next break. But Jaime is really awesome, knows a lot about NetSquid. So
yeah, feel free to ask me questions.
Go to him first. Okay, so example number 2. So the usual part, we first load all of the libraries. And so the goal for this one is send a classical bit, and then we will use this bit to do something to a qubit on the second node. So you can see how we're slowly building a teleportation program together, right? So we send a qubit before through the channel, so that the part here would be we're trying to distribute an entangled pair to two different nodes. And now we're using the classical channel to then transmit the information of a measurement. So that's also something we're going to need here. And you can see hopefully by now how there's always the same process. And that's kind of what we wanted to do with these notebooks. We wanted to show there is a system, and it's pretty easy to get caught up with this one, just because they're doing such a good job in providing so much material. Okay, so we always start with our physical instructions first, and we're initializing here 2 quantum processors that each just can store 1 qubit. So let's do this. And then we're assigning each processor again to a node. So this time we have node 2A and node 2B, but you see the difference. So we have port names again to get information in and out, but this time we called them CN and C out for classical information in, classical information out, so that we would know what kind of information is supposed to go to this one. Quick question from somebody: if the notebook can be run in Visual Studio Code. I have absolutely no idea. I think that's Windows, right? Visual Studio.
I'm pretty sure VS Code might have something to plug in for Jupyter notebooks. NetSquid itself, that should be fine.
It definitely works on Windows. Yeah, I think maybe not. I honestly haven't touched a Windows computer in probably 15 years, so I'm a horrible person. I know it's an editor, but I think most Windows people are using Visual Studio, whereas I'm on Mac. Sorry, we can come back to you hopefully on this one. NetSquid also has a port for submitting questions, even though I think they kind of stopped answering those recently. Okay, so now here are 2 nodes with the 2 ports. So let's run this one. And now comes the classical channel. So you can see it's very different to the quantum channel, and we will just use the predefined classical channel. And so let's go over the steps that we want to run through. We want to initialize a qubit in slot 0 on node 2A, and initialize a qubit in slot 0 on node 2B. So each of the 2 nodes will have their own qubit, because we're just trying to see how we can send a classical bit to then do something to a qubit on a different node, because that's the part we're focusing on right now. Then we will change the state of the qubit on node 2A to superposition state. We're only doing this so that to make it a little bit more fun, and it gives us another chance to practice applying another gate. So otherwise, if it's in the 0 state, we know if we measure, we'll get a 0. So at least this way, we don't know if we're going to get a 0 or 1. Then we will measure the qubit. We will send the outcome of this measurement through our classical channel to the other node. And then we'll have our conditional part again, where if that output, if the measurement outcome is a 1, we'll do something. And if the measurement outcome is a 0, we'll do something different. I think in this case, we do nothing when it's a 0, but there's another example where I think we apply different gates. And so what we need to do is we need to connect the nodes and the channel. This is very similar to the part before. The only difference is that this time we're not connecting a memory to the node and memory output, because we're just trying to send classical information. So we don't need to connect a qubit that comes out of the node to the port. We're just sending the outcome of a measurement. Then comes the part where we're initializing a qubit. And so we did this one. That was the qubit on node 2B, because we're not doing anything with this one. Then here we're using a little program to do a few steps together, just so we can practice with programs. So first, we get the indices and we apply the instruction to initialize a qubit. So now the qubit is initialized. Then we will apply the Hadamard to get the superposition. And then last here, we measure. And so whatever comes out of this measurement, we will store in this output key here. And that's what we're going to access afterwards. Right? So now we run the program on node 1A. This is the program that initializes the qubit, creates a superposition state, and then measures. So that takes a while because we're doing a bunch of things. And now we want to place the result of this measurement into the output port of node 2A. So here is the result. That's the output of the program, and we're storing it as M1. And now we're putting this one right into the output of the node. and then run this one. That didn't take any time because we didn't allocate any time for this process. Oh yeah, I did do two different things. And so now we're going to do this conditional part where we want to send the qubit and once send the classical bit, and once the classical bit is there, we want to use the classical bit to decide if we should do something or what we should do. If we're sending a 1, we want to say apply a Hadamard gate, and if we're sending a 0, we want to apply an X gate. This is not like the teleportation. We're just randomly choosing what to do if it's a 0 or 1. We're literally just trying out things. It's just similar to the teleportation, but there we have 2 measurement results. Okay. And now if you wanted, you could go ahead and peek at the state of the qubit, or you could measure this qubit, you could do some more. Our suggestions for you were to kind of combine the examples from the cases from example 1 and example 2. So create a quantum processor that has 2 memory positions for node A and one with 1 memory position for node B. And then you could send a qubit to node B, and then so node B doesn't have one until you send the qubit over, and then you could measure on a node A and then use this result to change the qubit on node B. So just ideas for things to try out if you want to practice some of this material. And I think I'm caught up on, everybody must have switched over to asking Jaime. Success. All right, so this was this one. So I will go back to my slides. Here we go. Share. Okay, example 3. So this is the last example for the quantum channel chunk. And after this, we only have 1 chunk left for quantum networks, and then we'll call it a day. And then we can, hopefully, I'll go through all of the questions, see if I missed anything there. Okay, so in this one, that's a really big one. That's really something we need if we want to do something networky. So the quantum programs are great, but the quantum programs run on a processor. And so it's just not enough. So we really want a quantum protocol that runs on a node. And then we can schedule much more complex things and really reach a better level of what we can simulate with this. So in this example, what we're going to do is the situation isn't more complicated. We're just using a new way to do it. So it's the same we did before. We have 2 nodes. We're just sending classical information. But what we want to do differently now, instead of doing what we just did, where we ran a protocol on a processor and then did the corrections afterwards, we want to use a node protocol where we tell the node all the things the node is supposed to do. So, this time I found it a little bit faster. We can close this one, and then we shut it down. And Jaime, how is the server doing? Is anybody still running?
Yeah, actually, we have quite a handful of people, and some of the newer people who joined late are currently using it, I believe.
Oh. Yeah, and just a reminder again, we'll leave it open so you can come back when there are less people and come back without having to install it all on your computer. Okay, so here is our example number 3. So the usual, we're loading everything. And this is what we want to do. So we're kind of using the similar example that we just did, but we want to use protocols for each node, okay? So we will first go through the typical motion and defining the physical instructions. And so if somebody says like, well, why do you have to redefine it all the time? You could have just had one big notebook and used them. Absolutely. We were just trying to create very standalone cases so that you also gain experience and become comfortable with all these different steps. So that was very much on purpose. Okay, so our instructions, then we have one processor that has 1 memory position and a second processor that has another memory position. Here are our 2 nodes. And since we're sending classical information, we only have the classical outputs and inputs for both nodes. There is the classical channel. So you see how we're starting to group more things into one, though, because we have now using them a few times. So all of these are things that we've been using in the previous notebooks. So if something is not clear, go back, play with them, and then come back to this. And then here is where we're connecting the ports of the nodes to the channel so that we have this one-way communication. Oh, there's one picture where the information goes through the channel. Oh, this is two-way connect. Okay, so let's run this one here. And so next comes the part where we have the quantum program. So this is something we've done before, right? So we have a program that just runs through these steps. We initialize a qubit. We create the superposition by applying the Hadamard gate, and then we measure. And so if you're looking at this and it's like, okay, this seems kind of silly, you could just send a number. Totally true. These are very much made up examples where we're just trying to have opportunities to practice. And so the reason for applying Hadamard is just to get superpositions. You could do something else. You could apply the Y gate or whatever you feel like, move around with, play around with it and just get some experience. So this is the program. That's what we want to run on node A. But now what will be different, before we ran this program directly on the processor, now we want to have something that we can run on the node, where we just say, this is a node, this node should do all these things. And if there are multiple nodes, they could do the same thing. And we would just say, hey, all these nodes run this protocol. So we have now a node protocol, and this node protocol will know the program we just defined, and it will execute it on the memory that's connected with this node or on this processor. And when it's done doing everything and it comes to the part where it's measuring, it stores the outcome of the measurement and stores it, sends it right away to the node output. So when I send this protocol to a node, whichever node it is, will do all these steps, calling the other program. And I forgot to actually run this stuff because I'm just talking. There we go. And then here's the protocol. And on node B, we're doing a lot less because here we really just want to have a qubit that's ready to take information, to be operated with. So this program is just an initialization program. And coming back to a question earlier where somebody was asking, can you have all these different parts? It's a good example, right? If you have a lot of things that you're doing, but on every node you're initializing, you could either put it in the programs or you can just have a program that does it and you just call this one line and that's the part. So there's definitely a lot of flexibility. Okay, so now we also write a protocol for node 3B. And first of all, what this will do is connect the, that's just defining, run the program that will initialize. So this is this part here. And then it will just sit there and wait for the message to come that the other node hasn't sent yet, right? We don't know when the node will send it. So it's literally just going to wait here for the input port to get this message here that's coming. And when it's there, then the message will be saved and evaluated. If the message is a 1, then it will, in this case, we will apply Hadamard. If the message is 0, in this case, we'll apply an X gate. So pretty much the last scenario, but all using a protocol. So now we have 2 protocols, and this is all we have to do now. I mean, I know it's not like we have less code, but there's more flexibility now, right? So we can run the protocol on node A and another protocol on node B, and then just start both of the protocols and start the simulation. And then we don't run into any problems with what is executed when and if they're in the right order, because this one, node A, will just do all the things it can do and send the measurements. And node B at the same time will go ahead, initialize the qubit, and then just wait until the results come. So let's run this. And the measurement outcome of our case here was a 1. So we actually applied an H gate, and the whole simulation took then 12 nanoseconds. And so now we're done with all of those. We can peek at the state. And we can see that this state is a superposition, which makes sense because we applied the Hadamard gate. So this was this example, the last example for channels. And so also the last notebook where we have practice suggestions, because we figured we will probably run out of time at some point. I'm sure you can come up with lots of things that you could try out. For this one, the idea was just try to practice a lot with processors and programs, and here are some ideas on what you could do. Okay, so let me close this one, and now we'll take our last 5-minute break, and then we have one more chunk for networks, and I'm guessing we will be done hopefully maybe 15 minutes early. That's the goal. We definitely won't run over. Okay, so I'll put in the chat that we will come back at, okay, let's do a weird one. 11:51 a.m. Arizona time, because that's exactly 5 minutes. And of course, then the time moved. It's fine. We'll come back at roughly 11:50-ish, and then we'll do the last chunk. And then we'll see if we can follow up with what we have left and questions, because I'm sure I overlooked some. Can you share this? All right, we'll pick up in a minute. Just looking through the chat, and there was one question: is this quantum channel physical? In previous modules, I said it was very hard to actually send a qubit across space or fiber. So this is exactly why we have these simulators, right? There are all these problems we still have to figure out. We can send a qubit through fiber, we can't send it for very far. And so the simulators all make assumptions, and they let us simulate certain more or less physical situations. For these examples here in the NetSquid, the channels overall is actually, everything is written very abstract. You're not even saying that you're sending a photon, you're just sending a qubit. And then by setting your parameters one way or another, you could make this abstract channel kind of behave like a fiber might, taking into account similar delay times, taking into account similar errors or loss probabilities. Sequence, for example, is very photon-based, so everything is in terms of photons. NetSquid is completely abstract, so that you just make your qubit what you want your qubit to be by setting the parameters accordingly. So hopefully that will answer this question. And yeah, so the process for extracting a qubit from the memory, then creating a photon in its state. So in NetSquid, this would literally just be popping the qubit out of the memory, putting it in the channel. So that's not included here. Sequence focuses on this. They have some examples where you're doing exactly that. Yes, communication shouldn't be faster than the speed of light. So in sequence, in NetSquid, the channels are abstract in the sense of just because it goes to a channel doesn't necessarily mean it's a physical channel that means it has to propagate. It could also just be a means from getting one thing into a different state, like a different location. They don't have to be physically separated, if that helps. And then there's one last question, then I'll go back. Licensing of NetSquid, is it limited to academic use? As far as I know, from what I remember, I signed up quite a while ago. All you have to do is go to the page and submit your email address. Is that correct, Jaime? And it is still completely free. I don't know if it will be free for forever, but at the moment, I think everybody can get an account and download NetSquid and then access everything. All right, so let's go to the last one. So here we go. So now we'll talk about, we're literally just putting everything together now. So we have all the components we need to look at this as a real network. And the first part we're focusing on, so maybe there's one more part we need, connections. So what this means here is we technically don't need to do that. It's just a cool thing to do or to have or to know how to do, because then you can do more complex things. So before we had the node, and the node was connected to a channel, and the channel was connected to another node. We're still looking at the same scenario in the next example. We're just describing it a little bit different because we're putting this channel inside a connection. And that seems completely weird when you look at it like this, because all you're doing is putting a box around a box and you're just sending it through empty things in a box inside the box. And that's because we didn't want to make this example more complicated, but down here is an example for what you could use this for. And this would be also much more realistic. Oh, this error should be the opposite way. See, there's a typo I have to correct. So normally when you would do teleportation, you wouldn't start with the qubits on one node entangling and sending it over. The idea is more that the two qubits start out with entangled, the two nodes start out with entangled qubits, but they still have to come from somewhere, but they don't necessarily have to come from one node. They could, for example, come from a quantum source that sits between the nodes and that consistently distributes entangled qubits to both of those nodes. And so you could have a source here that creates entangled qubits, and then it sends one qubit this way through a channel to this node. That's why this arrow should be the other way. And one qubit through this channel to this node. And then they both have their entangled qubits. Each of them has one of the entangled qubits, and then the teleportation could start. That's the more realistic scenario. And that's actually something that you can definitely model in NetSquid. You just, there's a source already built in. They also have an example where they use it. All of this could then be inside a quantum connection. So you just have a lot of things that you can put inside a connection, and then it's much smoother and cleaner to have the interfacing of the information, because you still have the connections have ports on both sides, and there is a lot of freedom in what you can do inside a connection. You could also have multiple channels to have in and out, like multiple directions in there. So this is the reasoning for why we're doing it. So let's do almost our last. That's it, right? Yeah. Okay, here we go. We only have, so we are at K, and then we only have 2 more left, and we will call it a day. Thank you all for hanging in there and being flexible. It wasn't exactly how we pictured it, but we'll make the best out of it. Okay, so the first step, the usual, loading everything. So this is summarizing what I just talked about. Instead of connecting channels directly, we will try to put a channel inside a connection, and then we connect this connection box to the nodes. So it seems very arbitrarily here, but it's an important component for more complex scenarios. So we wanted to make sure that we have it covered. Is it done? Yes, okay. Physical instructions. This is just the set of the things we want to be able to do. And we have 2 processors, each just has 1 memory slot. And then we will assign the processors to the nodes. And this part is still like we had it before. So node A has a memory, and the memory's output port will send whatever it gets right to the output port of the node. So that's like we had it before. And then node B has an input port, and whatever comes into this input port will go straight into the memory position, the memory storage it has. Okay, so we did this one. So before we used a channel, and we're still going to have a channel, but now the channel will be part of a connection. So this is the connections class. And so let me run this. So what we are doing, our connection is really, really simple. So this shows you what a toy model this is. The connection just has a channel. So it has the channel as before, but what we're doing differently is now we add the channel as a subcomponent to this connection and tell the code, the simulator, how we want the information to process. So what this says is here that the connection has an A and a B port. And so whatever comes into A should go into the send for the channel, and whatever comes in B will be the receive. Whatever is received from the channel will go into the output, which is called B. Okay, there we go. And there's our channel. And so the only different part is instead of connecting the nodes to channels, we're connecting the node to the connection. Sounds kind of funny when you're connecting a node to a connection. And then we have our programs before. So we've been sticking to the same ones. We're initializing a qubit in slot 0, and then we're creating, in this case, we're actually creating a plus state. I think that's what we were doing earlier too. And then we have a protocol that runs this, and it does a little bit more. It removes the qubit from the memory, and then it sends this qubit to the output port of the memory. And then we'll have a protocol for node B that just waits for this qubit. So here's our program and our corresponding protocols. So here are the steps that we want to be doing on node A. And here's the protocol that will do this. So this protocol right here calls the program, runs it, and then pops the qubit out of the memory after it changed the state. This qubit gets sent to the output port. And that's everything that's happening on node 1, node A. And then on node B, all we're doing here is wait. We sit here and we wait for a qubit to come. So the protocols. And then like before, we just run the 2 protocols. And we can see that in this case, it took 4 nanoseconds. And if we look at the memories, we can see the memory has now arrived. It's now on node B. There we go. And we can also check the state. Yeah, okay. So that's it. That was a quick one. There wasn't, I don't know if I missed anything. Oh, okay, we'll do the Q source. Okay, I can go back. I'm gonna I see some questions in the Q&A and I will come back to them. I think that will work perfectly. Next, please. Okay, so let me start with, there is a question about the quantum source. So I'll go back to the PowerPoint for this. Is the connection most likely a traditional switch or repeater? I will also do this with the PowerPoint. And then one last question, when you say protocols, what does this mean in context of NetSquid? Okay, let me answer this one with the code, and then the other two I will answer with the slides. So protocol here, and I should give some clarification to this. I am by training a theoretical condensed matter physicist. I'm not a network expert, and I'm also not a computer scientist. So if you find some parts that are programmed pretty funny, it's because this is a self-taught programmer who wrote a lot of this. And I think Jaime is also self-taught and is not a computer scientist. We're physicists, so we might program something sometimes not as efficiently as other people would. And it could also be that there are certain terms that have other meanings in other areas that I might not even know about. I think protocols are actually similar for classical networks. It might be wrong. So all this means in this case is that the node is the part that stores the memory and has the instructions for the processor. So you can picture it like a quantum computer, right? And the programs that would run on this the processor, like the quantum computer, the programs that run on these quantum computers, those would be the quantum programs. But then the node is more. The node is the quantum computer, plus this other framework of how to get information out of the quantum computer, how the connections, the links to other nodes, like the connection to the links. And so this is the part that's supposed to be run through the protocol. So then when you, for example, have it here, you can create a protocol that will just run on the node and then call things that will run on the processor. So the reason for doing is NetSquid has a lot of components and a very leveled system, and certain things can't talk to each other when they don't have the same hierarchy. So for example, I can't connect a channel to a memory. You can only connect a channel to a node, or you connect a connection to a node. And so certain things will not run on certain parts. And so the protocols that can run on the nodes offer you a convenient way on having a way of executing lots of programs that will run on the components of the nodes. Does this answer the question? I feel like I talked a long time and I'm sure I said anything. Please feel free to follow up if this helped or if this didn't help at all. I'm happy to give it another try. In the meantime, let me open the slides. Okay, so then the question was, oh, it helped. Yay, you made my day. Awesome, thank you. The functionality of the Q source. Okay. So this was just the example that I used to highlight why you might want to have a connection, in this case, a quantum connection. So picture a case where you have a source that, there, and we've talked about this in some of the other modules, there are different ways of untangling qubits or generating qubits, right? Entangled qubits already. And so in NetSquid, this quantum source gives you just an abstract way of providing these qubits. They're already entangled. And then it has a lot of opportunity for you to customize it to your needs. You can, for example, set with which rate the qubits are being generated. So the frequency with which they're coming out. And so this would be something you could model here. So this source would produce entangled qubits. And I think it was Ryan Camacho who talked about, for example, entangling qubits to down conversion. So you could do something like this. So the qubits come out here, they're entangled, and then they go one way to this node and one way to the other node. So this is really more how we picture this to work at some point. Hopefully this will work. And then, is the connection most likely a traditional switch or repeater? So the switches, I think, are more like nodes, but you would need these connections to make a quantum repeater, and you could put a lot of things inside your connection. I don't think you put a node inside a connection. So I might have to pass on this one. Jaime, if you know, feel free to jump in.
I'm sorry, can you repeat the question?
Is the connection most likely a traditional switch or repeater? I don't think that's the case. I think a repeater would be a combination of nodes and connections.
Yeah, so for you can have nodes.
Can you have a node inside a connection? No, I don't remember.
No, you can't have a node inside a connection. A connection specifically connects the ports of nodes to other ports.
Right, but you can have a source inside a connection. I don't think you can, so I have to go back on this one. But I would say that connections would be an integral part for building a repeater. And connection would not be a switch would more be like a node that has a specific quantum processor that allows you to do what it does.
Yeah, connection is more like the fiber, the wire, the channel that is connecting the nodes.
Right, but if you look at the picture here, like the class of connection is bigger than that, right? It can also have other components. All right, so let's go to the last two examples. So we have our first full network. So now we combine everything together, and then we run a full teleportation protocol. And so you probably get an idea what the last network, the last example will be. So this is what we're going to do. We have a node. Since we're not including a quantum source here, we thought that was going too far. We will have our node A starting out with 3 qubits. We will create our smiley qubit state, and we will then entangle these 2 qubits. We will take one of those qubits after they were entangled, send it through the quantum channel to node B, and then keep this over here. Then measure these other 2 qubits, and the outcomes of this measurement will go through the classical channel and then end up at node B. And we use this to then go from there and modify our qubit as needed. Okay, so that's the plan. Here, okay. Close this one. Oops, I have to close these. Okay, almost there. Thank you all for hanging in there. Probably a lot to go from network example to example to example. So run. And you can see it's getting longer and longer. I included the source here because I actually thought about putting it in and then I took it back out, but I forgot to remove this. So you wouldn't actually need to import the source here. You can see what's going to happen soon, delays and noise. Okay, so this is what we're going to do. All the steps I just went through. We will start with our physical instructions. We have to do a lot of things now. We have to initialize. We have all these different gates we have to apply because we're really starting to do a full teleportation protocol. So we have these, and we have topology in here. So we're saying we can do a control knot between the first 2 qubits and the last 2 qubits. We can't do a control knot between the first and the last qubit. There's nothing that forbids us from having it defined like it could. We don't need it for the teleportation program, but there might be scenarios where you wouldn't be able to do that. And then we have the quantum processors. And this time we're starting to have a lot of memory storage here. So each of these processors has 3 positions. That's total overkill. For the second one, we actually only need 1. I just kept it the same because I'm using the same instructions. There is the connection. We had those before. So we have our quantum connection. And this is like we had it before. And now we also have a classical connection. Very similar syntax. We're just sending, one time we're sending quantum information, one time we're sending classical information. And then here are so this is a new part. So now we're setting up all the components and we're combining them inside a network. It's not technically that we have to do that. It just makes everything a lot easier to move over to more complex situations. That's why we wanted to have it in. So we're defining a network and all the components that go into this network. So here are our 2 nodes. The node A has this processor here, node B has this processor. We know each of the processor has 3 memory storages, 3 slots. And this time we have a lot of ports because we have 2 ports for classical information, 1 in, 1 out, and 2 ports for quantum information. So we have those. Then we create this network, and then we add, this is just creating a network that's predefined. Then we add all these components to this network. So we add the nodes, and then we can target them. We can say node 1 in our network, node 2 in our network. We add the connections for the classical and the quantum information. And then very last, same as we did before, we tell the system in which way the information will pass through. So all these parts are really similar to what we did before. What's new is that we're now adding all of this as parts of the network. So we don't have it all separately defined anymore. And did it work? Yeah, okay, so that one worked. And so here are then the programs for the nodes. I think they're actually identical to the programs we did before. On node A, we initialize 3 qubits. we create our smiley state, and then we entangle the other two qubits. That's what's happening in this program. On node 2, I confused myself. Oh, that's the second program for node A, yeah. So this is the smiley state. What am I doing here? Oh, this is the belt state measurement again. Yeah, there are different ways of phrasing it, but I wanted to go here with the belt state measurements. Let's do this. The belt state measurement for qubit 2 and qubit 3, so we can get the results of the measurement. So this is what we're going to do here. So let's run these. Then we defined everything that is supposed to happen on node 2 program-wise. And those are the things we will want to call in our protocol now. So we will first call program 1, which initializes all the qubits and creates the entangled qubit pair. That's what's happening here. Once this is done, we take this one qubit out, this entangled qubit, and send it to the other node. That's what's happening here. And so once we're done with this, then we're in the scenario that we would normally start with, where our agent A has one half of the entangled qubit pair and agent B has the other half. And so now we're trying the teleportation part. So we do the belt state measurement. So we get the measurement results of those qubits and then send those out. And all node B does is waiting there for the qubit to get there. That's the entangled qubit, and also waiting for the message with the classical bits to come in. So it looks more complicated because it's just doing a lot more than before, right? But this is the quantum message that's coming. That's the actually entangled qubit that it needs to recreate this other qubit state. And this is the information from the other measurements. Let's run this. Okay. And then this is the actual instruction to run everything. So here is our network. We're defining it. Those are the two nodes that are part of this network. Those are the protocols for the nodes. And then we're starting the protocols, the one on node A and the one on node B. And when we're done, this is what happened. It took 50 nanoseconds, and the belt state measurement on the two qubits at agent A were 0 and 1, which means we applied an X gate to the qubit on node 2. So if we look, this qubit is there, and if we check the fidelity, it was still awesome. And it was still awesome, and that brings us to the next one, because we still haven't included any problems, right? We haven't included the possibility of losing a qubit. We haven't included the possibility of a qubit degrading, where it changes its state because it's sitting around so long. And a little bit of that comes in the last one now. Am I doing okay on, I don't think I missed anything. Okay, perfect. So let's do the last set of slides and the last example. And we still have a lot of you who are hanging with us. Thank you. Yes, slides. Here we go. Okay. Share. Our last one. So everything like before, but a little bit more realistic. And I put the realistic in quotation marks because it's still not very realistic, but you could make it much more realistic. So we have the scenario from before, but we're putting in some errors. For this one, we kept it relatively simplified, so you could include a lot more, but we are including some possibility to have a problem here. So let me go to those two. Yeah. Okay, the last notebook, M. Okay. So this is now where we're going to use the noise model and the fiber delay model. And it will happen in our processor. What we could do, what we didn't do, is we could have included also possibilities for errors in the instructions. Like we could say, when we apply a gate, there's a possibility that something goes wrong. We didn't do that here, but there is plenty of information on the NetSquared pages to add this. What we introduced in this one is just on one of the processors, we included a depolarizing noise model. What this means is, while the qubits are sitting in the storage and idling around, their state is going to degrade with a certain probability. And that's what we're counting for here. And the time of sitting around idling, that's really coming from the fact that the information has to be, like all of these steps has to be processed, right? The qubit has to be sent, the classical information has to be sent. So those qubits are sitting around. That's how we are including a little bit of realistic conditions in here. So I need to this one. Okay. The only part so we already have time for the gates. We didn't take into account how long it would take for the information to get through the channel. And so in this example, we're picturing a photon going through a fiber. And so for this one, we would then have to have a delay in the fiber, right? That would not be a realistic world if the qubit enters a fiber that's decently long and it's instantaneously there. So, and then I see there's a question about the units. Very good question. I have to get back on that. Did you look back, Jaime, if you were asking which units exactly? So the time was nanoseconds, and then the rates for the dephasing and the depolarization, I have to go back if it was nanoseconds or shorter than that or longer than that. Okay, so let me go through these real quick. Yeah, the depolarization units. We will get back to you on that one. From what I remember is the last time I looked into the description for the noise models, there were no units in the actual description of the functions, but they have to be somewhere. Otherwise, you can piece it back together because you know the units of the time, so you could backtrack. But I was actually surprised that I didn't see it like prominently. No, it's not a. What was it?
So the nice thing about the delay models is you can make your own and you can set the units however you want.
Right, but I thought it was a depolarization rate, not a ratio. That was the question in the chat right now.
Oh, I see.
Yeah, honestly, this is something I don't really work with. Some of my grad students might know more about the models. I think we have been working more with also making different models for some of those. But yeah, there is the good news is for this, you can completely define your own error models and just include them into your processor, into your physical instructions, and so model whatever you have in mind, depolarization, dephasing, or bit flips, anything. So in this case, we were using the predefined fiber delay model that just takes into account the length of the channel and then the time it takes, according to the length, to propagate through the channel. So we have the same model for the classical channel as for the quantum channel. So they're both supposed to be fibers. And this, of course, means that now we also need to give a length to the channel. And then we set up our nodes, create the network. So this is all the same as before. The only thing that's different is that the channels now have a length and that the memories now have a probability to depolarize the qubits. And so the last part is to run it. And so you would see here that for the first time, I actually set a seed number. And I'll explain why after I run it. I wanted to, so Python uses a random number generator, right? And so whenever you're doing these measurements, it will take the probability into account of how likely it is to get one result or the other, and then basically flip a coin. But you will always flip the coin in the same way, except if you change except if you set the seeds. No, if you fix the seed, then you will flip the coin the same way. So I wanted to have a case where this one example we're running actually results in a depolarized state. And I didn't want to include here what you normally should be doing at this point, which is run the simulation lots of times and collect all the data, because it just opens up a lot of other parts that are probably common to people who program a lot, especially with big data. But if somebody is maybe using Jupyter Notebook or Python for the first time, then maybe they don't need to figure out how to, it's like a data collector. So we just want to run at one time, but we wanted a case where the state will be depolarized. So we found one. For seed 47, it will work, or at least it worked before. So let's run it. Oh, I forgot to run this part. Okay, run this one. There's again. Okay. Now I have to run all of it. So doing this thing that I talked about earlier, do the restart and clear output to get rid of everything since I did stuff in the middle. And then I will just run the whole notebook at once so we can get to the end. This is a good example. So my family always teases me that when I talk, I stop, because apparently I can't talk and walk at the same time. So I don't stop every single time. Okay, now all of these are running. And done. Okay, this time it worked. And the fidelity is 0. Yes, awesome, perfect. Exactly the case we wanted. So we said it, if you would remove the seed part and just run it a bunch of times, you'll see that a lot of times the state actually didn't depolarize, the qubits didn't depolarize, and so you would get perfect fidelity. In this case, what happened was the state of the state that was teleported, it's a little bit harder to see here, is a little bit different from what you want. And it's not just different by a phase, right? So the gold state was this one here, 1/√-1. Oh, here, 1/√1, that's the gold state, but instead we got a -1i. And this one should have been an I over here. It's called on the spot correcting. Okay, so you can see that that's not just a simple thing. So this is not a state. Oh no, it was, yeah. So this is a case where the error effectively screwed it up. So the state that we wanted to teleport didn't end up at the node in the same way that it was supposed to get there. Okay, so I will close this and go back to the slides to finish up, and then I will see what other questions are there. But for all, we are done. 9 minutes to go. Perfect. Okay, just to summarize, and then I will look into the chat to see if there are any open questions. So the idea was to use this opportunity to help people who are interested in starting to use quantum network simulators for various reasons, maybe for teaching, maybe we're exploring, or maybe for really doing research in this area, or just for fun because you hear a lot about it and there is no physical internet that you could try all these things out on. And we wanted hopefully to provide you with material that you could take to then do something with this, build onto this, whatever area you consider useful for yourself. And even if it is manipulating qubits and measuring and getting a better feel for what entanglement means or something like this. If you want to keep using these notebooks, if you have run them on the server, you can download them from there. If you want to keep going, we will leave the server up for about a week, I think, and then we'll have to wipe all the accounts. So we'll give you about a week since this didn't work for everybody to run everything. If you want to go ahead and use it longer, just install NetSquid. There hopefully won't be any problems, and then we'll have the survey. And now let me look real quick if there was anything else. There was one more question in the chat. If the speed of propagation in the fiber depends on things like frequency refractive index, that would be up to your model. So you can define a model that will account for all of this, or you can have a pretty simple model that just has a simple matching where it says we're roughly expecting it to take this long. But you can make it as complicated or as simple as you want. All right, so if there are no more questions, then I think we'll call it. Jaime, any last words?
Yeah, if anyone is having issues with the notebooks or wants a fresh set of the notebooks or never got the notebooks, let me know and we can email those to you. Just send an email. I don't know if our email or information was up, Inés, but I can put it in the chat if anything.
Yeah, I'm also easy to find if you just go to the CQN page. I'm definitely listed there. I think my email is on there. Otherwise, NAU, I'm sure we have, we can provide this too. Otherwise, I'll put my email in the chat real quick and then you can see this too.
Yeah, if you need anything with the notebooks, feel free to reach out. They should be running. If anyone had any issues running or found an error, it might be, I don't know, there might have been just some small thing that got deleted. But if that's the case, we can always just send you new notebooks. That way you don't have to keep going and looking for where the error is yourself.
Yeah, and we will talk to Brianna. I think she is going to send out some information anyways, and we probably have a participant list for this course. And so we can have her send out all the notebooks together with the slides, and we can fix the few typos that were there. All right. Well, thank you all. Thanks everybody for being patient and hanging in there. And I hope you got something out of it, and that was fun. Bye.
Great, thank you, Inés and Jaime. Yes, we will get recordings and all of the supplementary documents sent out to all those who attended, and everyone should have a great weekend. Thank you.
Bye.